Welcome to the Masterclass, where we begin our deep dive into the Telecommunications Distribution Methods Manual and the core requirements for your RCDD certification. This chapter establishes the foundational baseline for your engineering journey through complex telecommunications infrastructure and global standards. This course is an unofficial, independently produced study guide. It is not affiliated with, endorsed by, or connected to BICSI in any way. This content is for informational and educational purposes only and does not guarantee success on the RCDD examination. All trademarks belong to their respective owners. Achieving the Registered Communications Distribution Designer credential is not merely about passing a test. It is about demonstrating mastery of the entire ecosystem of modern telecommunications. You are embarking on a path that requires deep technical knowledge of how voice, data, video, and building automation systems converge within the built environment. Throughout this course, we will dissect the Telecommunications Distribution Methods Manual to ensure you understand the rigorous standards that govern our industry today. You will learn how to design robust infrastructures that support everything from commercial data centers to specialized healthcare facilities. By the end of this curriculum, you will possess the analytical tools necessary to navigate complex design challenges and secure your credential on the first attempt. We will systematically investigate the historical evolution of network infrastructure, moving from legacy copper-based telephone systems to the high-speed converged networks that serve as the backbone of contemporary business. Understanding this transition is crucial because modern design is often constrained or informed by the architectural legacies we occupy. We will analyze the physics of transmission media, the mechanical requirements of pathway systems, and the critical importance of grounding and bonding protocols. Every lecture is designed to build upon the previous one, providing you with a mental model of how different subsystems integrate into a cohesive whole. We will focus on project administration, procurement processes, and the lifecycle management of telecommunications assets. Success in this field relies on an exacting adherence to industry regulations and the ability to apply engineering mathematics to real-world scenarios. We will explore the TIA and ISO IEC standard bodies, which provide the essential framework for all structured cabling and space planning activities. You need to understand how to size equipment rooms, design entrance facilities that meet current codes, and ensure that environmental controls protect sensitive hardware. Our approach emphasizes the strategic thinking required to handle firestopping, pathway loading, and cable support systems that withstand the test of time. While the manual is exhaustive, we will prioritize the core technical concepts that frequently appear in the exam blueprints. The RCDD designation is widely recognized as the pinnacle of professional excellence in the telecommunications industry, and your journey here is a commitment to that standard. We will examine how to approach the formal examination by breaking down complex problems into manageable engineering tasks. You will develop a methodology for site surveys, bidding, and construction administration that aligns with professional best practices. By focusing on the interplay between physical media and architectural constraints, you will learn to speak the language of both architects and contractors. This structure is intended to give you the highest possible probability of passing your exam and applying these skills in your daily practice. I look forward to guiding you through this comprehensive technical journey. See you in our next session on distribution design principles. Welcome back, and today we begin our exploration of the foundational principles that govern telecommunications distribution design within the BICSI framework. When we approach the design of a structured cabling infrastructure, we are essentially building a skeleton for information technology that must survive both technological shifts and physical degradation. The underlying premise is that a robust system is built on a hierarchical star topology, which offers the most predictable path for administration and troubleshooting. By isolating segments into logical tiers, we minimize the blast radius of a single cable failure or hardware malfunction. This approach demands that we respect the physical limitations of transmission media while simultaneously planning for the inevitable increase in bandwidth requirements. A professional designer does not simply connect arbitrary points. They construct a coherent ecosystem that treats the physical layer as a primary service, not an afterthought. Signal transmission is the heart of this discipline, and we must master the physics of copper and optical fiber to ensure data integrity over long distances. We measure performance through various metrics such as bandwidth, which defines the range of frequencies the cable can transport, and attenuation, which describes the signal power loss as it travels along the medium. Crosstalk remains one of the most critical challenges in copper systems, where near-end crosstalk, or NEXT, and far-end crosstalk, or FEXT, create localized interference that can compromise signal-to-noise ratios. By observing the attenuation to crosstalk ratio, or ACR, we gain a vital metric that tells us whether the signal remains usable by the time it reaches the receiver. We also track propagation delay and delay skew to ensure that data packets arrive in the correct temporal sequence, preventing the degradation of sophisticated high-speed protocols. Beyond basic signal integrity, a master designer must possess a firm grasp of transmission line theory and decibel mathematics. Decibels are our universal language, allowing us to describe power changes across complex networks without getting lost in unwieldy raw numbers. When we calculate insertion loss and return loss, we are essentially checking how much energy is being consumed by the cable itself versus how much is being reflected back to the source due to impedance mismatches. If we fail to manage these reflections, we induce signal degradation that renders high bitrate applications, like low-latency video streaming or industrial automation, completely unreliable. The Shannon-Hartley theorem serves as our mathematical North Star, defining the theoretical maximum capacity of any communication channel based on its bandwidth and noise levels, allowing us to validate our designs before a single conduit is ever installed. However, our duty extends well beyond the transmission of bits. We must account for the physical environment and electromagnetic compatibility. Electromagnetic interference, or EMI, can turn our cabling into an antenna that picks up noise from fluorescent lighting, motors, or power lines, while electromagnetic compatibility, or EMC, measures our system's immunity to these external stressors and its propensity to cause interference elsewhere. Effective mitigation strategies involve proper shielding, grounding, and maintaining adequate separation distances from potential noise sources, all of which are documented requirements in the TDMM. Furthermore, we must consider the environmental variables, temperature, humidity, and airflow, that impact the longevity and performance of the hardware housed within our telecommunications rooms. A design is only as strong as its most vulnerable link, and ignoring these variables is a shortcut to long-term operational failure. Integrating disparate systems into a unified infrastructure requires a vision of total systems harmony, ranging from traditional voice and data to modern building automation and security systems. As we move toward the Internet of Things, the physical layer must support non-traditional endpoints like smart sensors, building access controls, and automated climate systems. This convergence means that our cable pathways must be scalable, and our spaces must be modular enough to adapt to hardware upgrades without requiring a complete overhaul of the building infrastructure. We balance current performance needs with the necessity for future-proofing capacity, ensuring our clients receive a system that provides a return on investment for decades. It is this synthesis of mathematical rigor, electrical physics, and long-term architectural foresight that distinguishes an RCDD from a mere technician. See you in the next lecture. Welcome back. Today we are diving into the TIA and EIA standards that form the backbone of modern telecommunications infrastructure design. In the world of professional telecommunications design, standardization is not merely a suggestion. It is the fundamental language that ensures interoperability and performance. When we look at the TIA 568 series, we are examining the core requirements for commercial building telecommunications cabling. This standard provides the baseline for structured cabling, dictating how we transition from the telecommunications room to the work area outlet. It describes the physical parameters for twisted pair, optical fiber, and coaxial media, defining testing limits that every certified installation must meet. You must internalize these parameters, as they represent the legal and technical baseline for any project you might be responsible for certifying as an RCDD. Beyond the basic cabling requirements, we must integrate TIA 569 into our design methodology, which governs the logical layout of pathways and spaces. This standard is critical because it dictates how we provide adequate room for cables and equipment, ensuring that we never violate bin radii or tension constraints during the installation phase. Meanwhile, TIA 606 ensures that every component is properly labeled and documented, creating a manageable life cycle for the network infrastructure. Without a rigid adherence to TIA 607 for bonding and grounding, the entire installation remains vulnerable to electrical interference and safety risks. Furthermore, TIA here in 62 introduces the specialized requirements for intelligent building systems, highlighting the convergence of IT and building automation. Mastering these standards requires more than a casual reading of the documentation, as the devil is often found in the specific errata and addenda. For instance, the distinction between T568A and T568B pinout schemes is a trivial piece of knowledge in a vacuum, but choosing the wrong one during a multi-floor deployment leads directly to costly, time-consuming remediation. You need to develop a habit of mentally mapping these rules against complex architectural blueprints. When you look at a building layout, you should immediately visualize the path of the conduit, the presence of firestopping, and the necessary separation distances from EMI sources like power lines. This spatial awareness is the mark of a seasoned designer who understands that performance is guaranteed only when the rules are applied correctly in the field. Consider the constraints placed on copper cabling, where category performance is defined by transmission bandwidth and crosstalk mitigation. Legacy categories continue to exist in the field, yet our design decisions must balance the reality of current high-speed requirements against existing, older cabling infrastructures. You are expected to know the absolute maximum cable lengths for permanent links and the impact of environmental factors like heat on cable performance. When cables are bundled tightly, heat buildup can degrade signal integrity, a common failure point that is often overlooked by less thorough designers. If you do not account for these physical limitations, the integrity of the data transmission will suffer regardless of the hardware you choose to install. Finally, never underestimate the legislative weight carried by these North American standards in the context of professional practice. Following these guidelines ensures that your design meets safety regulators' expectations, protecting the human lives and capital assets housed within the building. As you study these standards, think less about memorizing definitions and more about why a specific parameter exists in the first place. Every limit, whether it involves pulling tension for fiber optics or the minimum width of a telecommunications room door, was established to solve a recurring technical problem. By understanding the intent behind TIA and EIA directives, you transition from someone who follows rules to an expert who enforces design excellence through rigorous, principled application of the industry code. I will see you in the next lecture. Welcome back. In this lesson, we will move beyond North American standards to master the global ISO and IEC 118.1 frameworks for generic cabling. To design telecommunications infrastructure for a multinational client, one must move past the TIA 568 mindset and embrace the ISO IEC 118.1 standard. While TIA categories define the performance of cabling components, ISO IEC defines performance in terms of classes, which describe the performance of the entire link or channel. A common point of confusion for designers is the assumption that a Category 6A component maps perfectly to a Class EA link. In reality, Class EA is defined by transmission parameters up to 500 MHz, but the international standard specifically focuses on the end-to-end performance of the permanent link or channel rather than individual component naming. Understanding this distinction is vital when specifying systems in regions where ISO IEC compliance is mandatory or preferred over TIA benchmarks. We must look closely at how Class D, E, EA, F, and FA correspond to their TIA counterparts, while noting the specific technical divergence, where TIA 568 uses categories 5E, 6, and 6A, ISO IEC 118.1 uses Class D, E, and EA to describe similar frequency envelopes. However, the divergence thickens when we reach Class F and Class FA, which encompass frequencies up to 600 MHz and 1000 MHz respectively. These classes effectively deprecate the RJ45 interface in favor of non-RJ45 connectors such as the GG45 or Terra interfaces. These connectors were specifically engineered to provide superior isolation and reduced alien crosstalk, which is a necessity when testing to the more stringent ISO IEC limits that often exceed standard TIA requirements. The permanent link and channel models under international frameworks serve as the foundation for all validation testing. When performing field testing for a global project, you are verifying that the complete system meets the specific insertion loss, return loss, and crosstalk limits mandated by the class. The EN 50173 series provides a European overlay that aligns with these international standards but adds specific requirements for electromagnetic compatibility and safety protocols relevant to European installations. As a designer, you must ensure that your bill of materials accounts for these regional mandates, particularly regarding shielding requirements. While UTP is common in North America, ISO IEC implementations often push towards SACE-TP, STP, or FTP to meet the stricter balance requirements inherent in international compliance. Grounding and shielding nuances represent a significant portion of the design complexity within the ISO IEC environment. Unlike many TIA-focused designs that rely heavily on unshielded twisted pair, an international design often requires a holistic approach to bonding the cable shield to the equipment in a way that prevents ground loops. You are effectively designing a grid that must remain consistent across different local electrical power grids and regulatory jurisdictions. When you specify a system, you are not just selecting a cable. You are selecting a transmission architecture that must remain valid whether the installation occurs in a data center in Frankfurt, a corporate headquarters in Tokyo, or a regional office in London. This requires a rigorous evaluation of the supply chain to ensure that the connectors, patch panels, and patch cords are all certified to the same international class. Ultimately, the goal is to create a seamless infrastructure that ignores geographic borders, yet respects local standards. Your role as a designer involves bridging the nomenclature between TIA categories and ISO classes, while ensuring that your testing equipment is configured to verify the correct international standard. By standardizing on Class EA or higher, you provide a resilient physical layer capable of supporting current and future high-speed applications regardless of the global location. Always remember that the validation of a link is not solely an end-of-project checklist item, but a critical verification of the design intent expressed through the international framework. This ensures that the telecommunications grid is not only compliant, but also interoperable across the entire multinational footprint of the corporate entity. I will see you in the next lesson. Welcome back to our discussion on the foundational standards that govern the telecommunications industry. Today, we turn our attention to the National Electrical Code, an essential framework for ensuring safety and compliance in all low-voltage installations. The National Electrical Code, or NFPA 70, serves as the benchmark for electrical safety in the United States and heavily influences global standards. For the RCDD candidate, navigating the legalistic language of this document is not merely an academic exercise, but a professional necessity. We focus primarily on the articles that dictate how communications infrastructure interacts with the built environment, specifically regarding fire safety and electrical interference. Article 800 forms the backbone of our discussion, as it outlines the general requirements for communication systems, including circuit integrity and grounding. Understanding these mandates ensures that the copper and fiber optic systems we design do not inadvertently become hazards in the event of a building fire or electrical surge. We must respect the intent behind these articles, which is to protect life and property by preventing the spread of fire and smoke through telecommunications pathways. When we examine Article 770 regarding optical fiber cables and raceways, we see a distinct focus on the physical properties of the medium itself. While fiber is dielectric, the cables themselves often contain strength members and jacketing materials that can contribute to fire spread if not properly rated. This is where the hierarchy of flammability ratings becomes critical to our design decisions. We categorize these cables into plenum-rated CMP, riser-rated CMR, general-purpose CM, and residential-grade CMX. A plenum-rated cable is mandated for use in environmental air handling spaces because it exhibits low smoke and heat release characteristics. Conversely, using a lower-rated cable in these spaces is not just poor practice, but a direct violation of code that could lead to significant legal and safety repercussions. Always verify the marking on the cable jacket against the specific location of the deployment to maintain strict adherence to the code. Managing power-limited circuits requires a different set of rules, which brings us to Article 725. This section governs Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. In many modern intelligent building deployments, these circuits carry both power and data, essentially blurring the lines between traditional telecommunications and electrical power distribution. You must ensure that the insulation levels and current limiting power sources are compatible with the intended application to avoid overheating or arc faults. These circuits must be separated from light and power circuits unless the insulation of the power-limited circuit is rated for the maximum voltage that could be present. Proper separation maintains the integrity of the data stream and prevents power surges from migrating into your communications equipment. Beyond cabling, the code mandates strict requirements for the protection of the building entrance. We must implement a comprehensive grounding electrode system at the point of entrance to dissipate transient voltages from lightning or external power contact. The connection to the grounding electrode system must be robust, usually via a grounding conductor that meets the minimum sizing requirements outlined in the electrical tables. Furthermore, we must maintain specific clearance distances between telecommunications cables and unshielded electric light or power circuits to prevent inductive coupling. These physical separation requirements are calculated based on the voltage potential of the power lines. When working within tight telecommunications rooms or shared pathways, failing to respect these clearances is a common point of failure for designers and contractors alike. Finally, we must address the mechanical aspects of pathway design, specifically conduit fill capacities found in Chapter 9. Many designers make the mistake of assuming that the physical size of the conduit is the only limiting factor. Instead, the code relies on percentage fill tables that account for the cross-sectional area of the cables relative to the internal area of the conduit. If you pack a pathway beyond these percentages, you risk damaging the cable insulation during the pull and interfering with future maintenance. Additionally, we must consider the heat dissipation capacity of the conduit, which decreases as the fill percentage increases, potentially impacting the performance of high-bandwidth copper links. By strictly calculating these fill ratios, you ensure that the installation remains maintainable and compliant for the life cycle of the telecommunications plant. I will see you in the next lecture. Welcome to this chapter on safety regulations, where we will examine the National Electrical Safety Code and its critical role in infrastructure design. We are going to explore the NESC standards governing the placement, maintenance, and operation of communication lines within the outside plant environment. The National Electrical Safety Code, published by the IEEE, serves as the fundamental framework for ensuring safety when dealing with electric supply and communication lines. As an RCDD, you must view the NESC not merely as a set of suggestions, but as a rigorous standard that dictates how we navigate the inherently hazardous intersections of power and communication systems. When designing outside plant architectures, you operate in an environment where contact with high-voltage lines is a constant, physical reality. Compliance with Parts 1 through 4 of the NESC is legally mandatory in many jurisdictions, and it provides the technical authority required to defend your design decisions. This code defines the rules for how communication infrastructure interacts with existing utility grids, ensuring that both the technicians working on the lines and the public are protected from arc flashes, induction, and physical contact. Understanding the nuances of these rules is what separates a novice designer from an expert capable of engineering resilient backbone systems. One of the most critical aspects of the NESC involves the precise clearance metrics required for aerial and underground installations. When you design an overhead crossing, you must meticulously calculate the clearances between communication cables and supply lines, keeping in mind that these distances change based on voltage levels. These requirements are not static. They are highly sensitive to NESC loading districts, which categorize geographic regions based on expected heavy, medium, or light ice and wind loads. You must account for how environmental stressors affect sag and tension on messenger wires, as a cable that meets clearance requirements on a sunny day may violate them during an ice storm. The physics here are uncompromising, as improper tension management can lead to excessive loading on utility poles, potentially resulting in catastrophic structural failure. Every design must include a thorough assessment of these environmental variables to ensure that the installation remains compliant throughout its entire operational lifecycle. Failure to apply the correct load multipliers for your specific region can render an entire project non-compliant, necessitating costly and complex remedial work on existing utility infrastructure. The concept of joint use or shared utility poles introduces complexity into the make-ready engineering process, which is essentially the preparation work required before new cables can be attached. You must coordinate with power utility companies to ensure that every pole involved has sufficient structural capacity to support the additional load of your communication infrastructure. This process involves formal pole attachment agreements that stipulate exactly where your hardware can be placed relative to the power supply conductors. If a pole is deemed insufficient, the design must account for replacement or reinforcing, such as the addition of specific guying and anchoring systems to counter the pull of the cables. These anchors must be positioned to prevent the pole from leaning, which would otherwise alter the meticulously calculated ground clearances. Your ability to navigate the politics and engineering requirements of these agreements determines the feasibility of the entire outside plant route. It is a process that demands both technical proficiency in mechanical load calculations and strong project management skills to align multiple stakeholders. Beyond physical clearances and structural loads, the NESC sets strict mandates for the bonding and grounding of communication systems to mitigate hazards from lightning and power faults. In an aerial plant, you are required to bond shielding and messengers to the grounding system at specific intervals to ensure that any potential difference between the communication cable and the earth is neutralized. For underground installations, metallic cable shields must similarly be bonded to provide a controlled path for fault currents, preventing the cable from becoming an energized hazard to personnel. These intervals are not arbitrary. They are derived from a deep understanding of fault current magnitudes and the resistance of the surrounding soil. When you design these systems, you are essentially creating a safety shunt that protects sensitive information transport equipment from the catastrophic effects of power surges. If these bonding requirements are ignored or executed poorly, you expose the communication system to ground loops and safety violations that could lead to equipment damage or injury. Rigorous adherence to these grounding intervals is the final line of defense in maintaining a legally compliant and objectively safe outside plant design. I will see you in the next lecture. Welcome back. Today we are diving into the practical application of building codes and cabling standards to create unified, compliant design solutions. In the professional world of telecommunications design, abstract knowledge of standards is insufficient. You cannot simply memorize what is written in the Telecommunications Industry Association or International Organization for Standardization documents and expect success in the field. Instead, you must learn to synthesize conflicting requirements while respecting the immutable laws of physics and local legal mandates. When we design a cabling system, we are balancing high-performance data needs against basic life safety regulations. The hierarchy is always clear. Life safety codes, such as those governed by the National Electrical Code, always take precedence over performance standards like TIA 568. When you navigate a project, you are expected to resolve these tensions, prioritizing the safety of occupants before optimizing for throughput or budget density. The primary challenge in modern design is the role of the authority having jurisdiction. You may encounter a scenario where a local municipal amendment is more stringent than the national electrical or building code. Experienced designers understand that the authority having jurisdiction has the final say on the enforcement of safety protocols on a job site. Failing to account for these localized mandates results in stalled inspections and costly change orders that can compromise an entire contract. You must treat every design document as a legal instrument that proves your due diligence in adhering to both the spirit and the letter of these requirements. This means explicitly citing the codes and listing documentation for every component in your specifications to ensure that the installation reflects the design intent. Validation of components is another critical area where designers often fail during the commissioning phase. We rely heavily on independent testing laboratories such as Underwriters Laboratories or Intertek ETL to certify that our cabling media and hardware are fit for purpose. When specifying products, your documents must state that all materials meet the necessary safety and performance listings. A common mistake is selecting a path or a connector based solely on technical performance without verifying fire rating compliance. If you specify a cable jacket that does not meet the plenum requirements for an air handling space, you are creating a liability that no amount of link performance can justify. Rigorous documentation of these listings for every device in your system is non-negotiable for project sign-off. Consider the complexity of designing for a large-scale data center versus a healthcare facility. A data center requires high-density cooling and complex grounding, while a hospital demands stringent fire-stopping and infection control measures. In every environment, your goal is to flag potential non-compliant pathways or improper topology before a single cable is pulled. This is the synthesis we are discussing today, where you apply your technical understanding to physical reality. You are effectively performing a forensic analysis of your own design, checking for grounding loops, improper bin radii, or hazardous pathway loading before it manifests as an operational failure. By internalizing this process, you ensure that every engineered solution you provide is robust, legally sound, and physically capable of long-term survival. See you in the next lecture. Welcome back to our journey toward RCDD certification. In this chapter, we will master the essential architectural integration required to embed robust telecommunications infrastructure into modern construction projects. Building a career in telecommunications design often feels like a constant struggle against the limitations of physical space. You have likely experienced the frustration of trying to shoehorn a high-density equipment rack into a room initially designed as a janitorial closet. This chapter changes that paradigm by teaching you how to secure the necessary square footage during the early schematic phase of building design. By mastering the principles of space programming, you will position yourself as an indispensable partner to architects and mechanical engineers. This course provides the rigorous methodology you need to defend your infrastructure requirements against competing interests in the design phase. We will begin by exploring the strategic necessity of involving telecommunications planners as soon as the building footprint is established. Integration is not merely a matter of convenience, it is a fundamental requirement for building performance. If you fail to advocate for your space requirements early, you inevitably compromise the physical layer that supports all subsequent network operations. We will examine the specific professional relationships you must cultivate with structural, mechanical, electrical, and plumbing consultants to ensure your distribution systems are accounted for before the architectural schematic becomes rigid. This coordination is the difference between a functional, future-proof building and a project plagued by change orders and performance bottlenecks. Understanding the functional distinctions between various telecommunications spaces is the bedrock of our design methodology. We will define and contrast the specific roles of the entrance facility, the main terminal space, the equipment room, and the various telecommunications rooms and enclosures. Each of these spaces carries unique requirements for environmental control, physical security, and structural capacity that you must articulate clearly to the design team. We are going to look closely at floor loading capacities, ensuring your designs account for the substantial weight of UPS battery arrays and high-density server racks. You will learn how to communicate these technical needs in terms that structural engineers respect, specifically focusing on pounds per square foot ratings and floor structural integrity. A significant portion of our time will be spent mastering the spatial constraints that define successful horizontal distribution. We will focus on the interplay between floor height, ceiling clearance, and the practicalities of cable pathways that must eventually feed into these spaces. You must be able to design for the 90-meter permanent link limit consistently, and that requires a deep understanding of room placement relative to the user areas they serve. We will break down how to optimize room location to minimize horizontal cable runs, thereby preventing the common performance degradation issues that arise when designs ignore the physics of copper wire. By adopting these master planning concepts, you move from being a reactive installer to being a proactive architect of the building's digital nervous system. See you in the next lecture. Welcome back. Today we examine the technical requirements for sizing and localizing telecommunications rooms within modern commercial facilities. Designing a telecommunications room is an exercise in constraint management, where mathematical precision meets physical reality. The foundational rule of thumb mandates that a telecommunications room should occupy approximately 1 percentage point of the total usable floor area it serves. While this serves as a solid starting point for conceptual design, you must ensure that your calculations account for specific variables like equipment density and projected future growth. For instance, if you are designing for a floor plate of 10,000 square feet, you should plan for a room size of approximately 100 square feet. However, simply adhering to this ratio is often insufficient if the facility has high-density data requirements or specialized cabling needs. You must treat this square footage as a minimum baseline rather than a static goal. as scaling back space often results in an inability to service the equipment properly later. Always verify that your dimensions accommodate the essential rack units, which are defined as 1 3/4 inches of vertical space, while also allowing for the necessary horizontal cable management footprints. Refining the placement of these rooms requires a deep understanding of horizontal cabling limits, specifically the 90-meter distance limitation for permanent links. If you position the telecommunications room centrally within the floor plate, you effectively minimize the length of all horizontal runs, which helps maintain signal integrity and reduces the total cost of cabling. When a room is pushed to the periphery of a floor, you risk exceeding that critical distance, requiring you to implement additional intermediate distribution points, which complicate your network topology. You should map your floor plan meticulously, measuring the distance from the room to the furthest outlet in every quadrant to ensure compliance with relevant standards. Geographic centering is not merely a design preference, it is a vital engineering requirement to ensure that no drop exceeds the rigid distance thresholds established by current telecommunication standards. Consider how structural columns or existing mechanical shafts might obstruct your cable paths, as these elements often dictate the final, practical boundaries of your telecommunications room. Beyond floor area, the internal environmental requirements are just as stringent as the physical layout. Every wall must be lined with 3/4 inch, fire-retardant treated plywood backboards to allow for secure mounting of termination hardware and cross-connect fields. You must confirm that this plywood carries a legible stamp indicating its fire rating, as building inspectors will prioritize this safety feature during their final site visit. Furthermore, the space must be entirely devoid of foreign piping, such as water lines for fire sprinklers or HVAC ductwork, to prevent catastrophic damage from leaks or condensation. Structural floor loading must also be addressed, as floor-mounted cabinets, especially those populated with heavy copper cabling or uninterruptible power supplies, can quickly exceed standard office load specifications. It is your responsibility to verify with the structural engineer that the floor assembly can support the concentrated weight of high-density telecommunications equipment. Access and lighting are the final pillars of a functional telecommunications room design. ADA compliance requires that you provide enough clearance at the front and back of racks to allow for maintenance, usually a minimum of 3 feet or 1 meter of clear space. For the lighting installation, you should aim for a minimum of 50-foot candles at the mounting surface of the racks to ensure that technicians can read labels and verify port status without visual strain. You are also tasked with considering the volumetric capacity for the future, as data demands typically grow at a predictable, albeit rapid, trajectory over the life of a building. Do not design for today's capacity. Design for the inevitable expansion of ports and the inevitable migration to more robust optical media. If you fail to account for these clearances and power needs early in the project phase, you will find yourself dealing with unmanageable cable tangles and cramped, inaccessible workspaces that undermine the reliability of the entire installation. See you in the next lecture. Welcome back, as we explore the crucial design considerations for high-density network environments. Today, we focus on the equipment room, often referred to as the heart of your IT infrastructure. Designing an equipment room requires a disciplined architectural approach that prioritizes longevity and absolute reliability. We must carefully select a location that bypasses common physical hazards, such as proximity to water piping, high vibration equipment, or external walls vulnerable to environmental extremes. Avoiding electromagnetic interference is a non-negotiable design constraint, meaning we must distance our core switching and PBX systems from elevator motors, high-voltage transformers, or medical diagnostic tools like X-ray machines. These sources introduce noise that degrades signal integrity across sensitive backbone cross-connects. Furthermore, structural integrity matters. We must evaluate the room's placement regarding seismic zones and ensure flooding risks are mitigated by elevating critical hardware. If the building is located in an area with a high water table or known flood risks, the equipment room must be positioned above the floodplain. A well-designed room acts as a fortress, protecting the core assets that keep the entire enterprise functional day and night. Environmental controls within the equipment room must be managed with cold, hard logic rather than guesswork. High-density server deployments generate significant heat loads that demand professional-grade precision cooling solutions, such as computer room air conditioning units. These systems are not merely standard air conditioning. They are dedicated, 24/7 units capable of maintaining stringent temperature and humidity set points. We effectively manage this heat by implementing cold aisle and hot aisle containment strategies, which prevent the mixing of supply and return air. This separation ensures that cold air reaches the intake of the servers directly, while exhaust air is efficiently captured and returned to the cooling units. Because these systems run continuously, redundancy is essential. We typically size them such that if one unit fails, the remaining capacity can sustain the heat load without causing a thermal shutdown. Relying on shared building HVAC systems is rarely acceptable if performance targets for the equipment need to be met consistently. Power provisioning follows the same philosophy of rigorous risk reduction and redundancy. Every piece of equipment in the room relies on stable, clean electricity, which requires robust multi-phase power distribution units distributed strategically throughout the racks. We must calculate the total heat dissipation and power consumption based on the maximum equipment density rather than current usage to ensure the infrastructure does not become a bottleneck. An uninterruptible power supply system must be integrated to bridge the gap during utility power transitions, with battery strings sized appropriately for the load duration requirements. Beyond the UPS, the transition to emergency generator power must be seamless, achieved through automated transfer switches that isolate the internal load from the utility grid during outages. This multi-layered approach ensures that even in the face of local power instability, the equipment room maintains operational availability. Grounding and bonding requirements must be strictly adhered to alongside these electrical setups to ensure safety and prevent electrical noise from interfering with data transmission. Physical security acts as the final perimeter of our design strategy and should never be treated as an afterthought. Restricting access to the equipment room is critical, necessitating the use of multi-factor authentication, such as biometric scanners or smart card readers, to log every entry. For mission-critical environments, a Montrap configuration provides a secondary layer of physical security, preventing unauthorized tailgating into the secure space. Fire suppression strategies must prioritize equipment safety over traditional water-based sprinklers, which would be disastrous for electrical hardware. Clean agent systems, commonly FM200 or Novec 1230, are the industry standard because they extinguish fires by removing heat or oxygen without leaving residue or causing damage to sensitive electronic components. By integrating these physical, environmental, and security layers, you create a facility that is robust enough to handle the demands of a high-density network backbone. Each detail contributes to the overall availability and reliability required for RCDD level certification. See you in the next lecture. Welcome back to our exploration of telecommunications infrastructure design. In this session, we will focus on the fundamental principles of designing robust entrance facilities. The entrance facility, or EF, serves as the primary gateway where outside plant cables interface with the internal building backbone, effectively functioning as the demarcation point for all data streams. Design considerations here must be meticulous because this space acts as the first line of defense for the entire building against external environmental threats and electrical hazards. You must consider the pathway of entry, whether it is aerial, underground, or direct buried, as each requires specific mechanical protections. When penetrating foundation walls, you are required to use rigid water sealing mechanisms and specialized transit systems that maintain the structural integrity of the wall while preventing ingress of water, gas, or pests. Using core drills rather than makeshift manual openings ensures that the conduit paths are perfectly sized and sealed with link seals, which are essential for maintaining the environmental envelope of the building. Think of this as the physical firewall of your network architecture, where professional-grade sealing prevents long-term degradation of the cable plant. Safety protocols mandate the inclusion of a primary protector block that contains voltage surge suppression devices, typically utilizing gas tubes or solid-state electronics to handle transient surges. These protector devices must have an ultra-short, low-impedance connection to the telecommunications main grounding busbar or TMGB to be truly effective during a lightning strike or an external power utility surge. If the connection path to the grounding busbar is too long or has too many bends, the inductive impedance will prevent the surge from dissipating safely, potentially damaging downstream equipment or endangering personnel. You should design this connection with a minimum bend radius and the shortest possible run to ensure that the surge arrestor functions exactly as intended by the manufacturer's specifications. This grounding architecture is non-negotiable for RCDD certification because it transforms the entrance facility from a simple transit point into a managed protective system for the entire building. A significant aspect of your design burden involves transitioning from the rigid, often unlisted outside plant cables to the flexible, flame-retardant cables required for interior building spaces. The National Electrical Code imposes a strict 50-foot rule, which limits the length of unlisted outside plant cables that can safely enter a building without being transitioned into listed, plenum-rated, or riser-rated cabling. You must plan for the necessary transition splices at or near the entrance location, ensuring they are contained within secure, accessible enclosures that allow for future maintenance and cross-connect provisioning. This location must also accommodate the specific space requirements of your carrier service providers, who will terminate their equipment and provide the initial demarcation for the building's connectivity. Designing for this interface requires balancing the physical space needs of multiple service providers while ensuring they each have adequate working clearance and logical separation for ease of daily operations. Beyond physical protection and grounding, the functional design of the entrance facility must account for accessibility and future scalability. You should consider the placement of telecommunication spaces relative to the entrance point to minimize the backbone length and ensure efficient routing paths through the building core. This involves not only planning the current cabling load, but also anticipating future capacity requirements, as data bandwidth needs typically increase over time rather than remaining stagnant. Furthermore, enforcing strict environmental controls, such as regulating temperature and humidity, helps protect the sensitive carrier equipment from the stresses that might occur at an outer building perimeter. As a designer, your duty involves documenting these pathways and ensuring that your rack layouts permit logical cross-connection of the incoming circuits to the internal distribution system. When these elements are integrated correctly, the entrance facility becomes a seamless, code-compliant, and resilient gateway for all global data entering your facility. I look forward to seeing you in the next lecture. Welcome back. Today we examine the critical logistical considerations for telecommunications space placement and accessibility within a modern architectural footprint. Effective spatial coordination begins with the strategic vertical stacking of telecommunications rooms. When these rooms align vertically across floors, you create a dedicated, linear pathway for the backbone cabling system, which significantly reduces the total required cable length and lowers latency. More importantly, this alignment minimizes the complexity and associated costs of core drilling and subsequent fire-stopping procedures. Each core penetration through a floor slab is a potential weak point for fire safety and structural integrity. So consolidating these penetrations into a vertically aligned stack is an exercise in both efficiency and risk mitigation. If you find yourself designing a building where vertical alignment is impossible due to architectural constraints, you are essentially forced into a more expensive offset design that complicates cable management and increases material overhead. This is why professional designers prioritize location stacking early in the schematic phase of building design to avoid these technical hurdles later in the construction process. When we shift our focus to multi-tenant buildings or sprawling campus environments, we encounter the distinct challenge of shared versus dedicated spaces. In these scenarios, you must advocate for secure compartmentalization, particularly when demarc extensions must traverse areas occupied by other tenants or sensitive functions. Deploying secured cages or independent enclosures is often the only way to satisfy the contractual requirements of separate entities while maintaining the integrity of the telecommunications infrastructure. You have to consider every point of failure where unauthorized access could occur, making the physical hardening of these spaces just as important as the electronic security measures. This architectural discipline requires you to balance the need for accessibility with the reality of building multi-tenancy access rights. Without clear demarcation and controlled entry points, you inevitably face security vulnerabilities that could compromise the entire backbone distribution system. A often overlooked but critical aspect of this discipline is the logistical pathway required for installing massive equipment. You must verify that your designated telecommunications rooms and hallways can accommodate the physical transit of heavy gear, such as high-density core switches or lead-acid battery cabinets. Before you finalize a floor plan, you need to verify elevator load capacities, analyze the dimensions of the loading dock, and calculate the turning radii throughout the building's corridors. It is an unfortunate but common reality that an impressive design fails in the field because a piece of hardware simply cannot fit through a corner or a door frame. Rigging requirements for oversized equipment must be part of your early planning, as these logistical constraints often dictate where an equipment room should be placed in relation to the primary building entrance. If the hardware cannot reach its destination without being disassembled, you have failed to account for a fundamental physical constraint of the facility. Perhaps most importantly, you must enforce the requirement for 24-hour unescorted access for authorized IT personnel. The placement of a telecommunications room inside a restricted zone, such as a secure vault, a biohazard lab, or a specialized research area, introduces unnecessary administrative friction that can prevent timely emergency maintenance. When a service outage occurs in the middle of the night, your team should not need to petition security clearance from another department just to access the hardware responsible for network availability. This is why national standards emphasize that these spaces should be located in common areas that provide both physical security and operational independence. Prioritizing this accessibility is not merely a convenience, but a core element of maintaining the operational uptime of the entire enterprise infrastructure. You must treat this requirement as non-negotiable during your discussions with architects and stakeholders to ensure future upgrades and emergency repairs proceed without interference. See you in the next lecture. Welcome to the chapter on environmental controls and physical security, where we define the critical requirements for maintaining protected telecommunication spaces. This module provides the technical foundation necessary to safeguard high-density networking equipment from thermal stress and unauthorized access. In this chapter, you will master the precise requirements for environmental systems and physical security protocols, ensuring your designs meet the stringent criteria mandated for telecommunication spaces. We will explore the conversion of electrical wattage into sensible heat loads, ensuring your HVAC selection prevents thermal failure in critical environments. Beyond climate, you will learn to implement nested security layers, incorporating intrusion detection, automated access control, and specialized fire suppression systems. Passing this exam requires a mastery of these protective matrices to guard physical infrastructure against environmental and human-made threats. Join us to elevate your design expertise and secure your path to RCDD certification by mastering the infrastructure that keeps data centers operational regardless of external conditions. The primary objective of environmental management within a telecommunications room is to ensure that active hardware operates within the manufacturer's specified temperature and humidity ranges. We start by calculating the heat load, which is fundamentally derived from the power consumption of the equipment installed in the racks and cabinets. Since every watt of electrical power consumed by a server or switch eventually dissipates as heat, we use the conversion factor of 3.412 British thermal units per hour for every watt of power. If you have a total load of 2,000 watts, you are generating approximately 6,824 BTUs per hour, and your HVAC system must be sized to remove this specific sensible heat load. However, the calculation is not merely about capacity, but also about the quality of the air being supplied to the space. Maintaining a positive pressure environment is a non-negotiable requirement to prevent the ingress of dust, particulate matter, or moisture that can lead to hardware corrosion. The airflow must be properly managed using hot aisle or cold aisle containment strategies to avoid the mixing of intake and exhaust air, which can otherwise trigger cooling inefficiencies. Relative humidity should generally be maintained within a tight range, typically between 40 and 60%, to mitigate the risks associated with electrostatic discharge or condensation on sensitive circuitry. Physical security requires a tiered approach, often described as concentric circles of protection, starting from the building perimeter and moving inward to the individual equipment cabinet. The goal is to delay and detect unauthorized access attempt before a threat actor reaches the critical path or the networking electronics themselves. At the room door, industry standards dictate the use of robust hardware such as mortise locks and continuous hinges that are resistant to prying and physical force. Electronic access control systems using smart cards or biometric authentication should be integrated into the door hardware, with all activity logged back to a centralized management system for audit purposes. Beyond door hardware, we deploy integrated intrusion detection systems that monitor for improper entry, unauthorized motion, or tampering with cabinets. Video surveillance adds another vital layer of security, where cameras should be positioned to provide clear, high-resolution coverage of all entry points and high-value equipment aisles. These systems are most effective when they provide pan-tilt zoom functionality or fixed dome coverage that links activity alarms to the recording system, allowing for real-time verification of security breaches. Fire protection in telecom environments requires a departure from traditional water-based sprinkler systems to prevent collateral damage to electronic components. We utilize very early smoke detection apparatus, or VESDA, for its ability to detect the combustion particles of smoldering materials long before a traditional smoke detector would activate. This allows for early intervention, often before a fire has even fully ignited, protecting the mission-critical assets from both direct heat and subsequent cleanup efforts. When protection of the equipment is paramount, we turn to clean agent fire suppression, which uses specialized gaseous chemicals that absorb heat or interrupt the chemical chain reaction of fire. These systems are designed to reach a concentration level that suppresses the fire completely without leaving any residue, thereby allowing the equipment to remain operational or be brought back online quickly. The design must also account for room sealing integrity, as the effectiveness of the gaseous system depends upon its ability to maintain the required concentration for a sustained discharge period. By integrating these detection and suppression technologies, we create a secure, autonomous environment that protects infrastructure against both thermal degradation and the catastrophic potential of fire, ensuring long-term resilience for the networking hardware housed within. See you in the next lecture. Welcome back to our journey toward RCDD certification. In this chapter, we will examine the physical arteries of the telecommunications network and the fundamental principles governing reliable pathway design. Designing a telecommunications pathway system is rarely about simply getting a cable from point A to point B. It is an exercise in engineering constraint management where we must balance physical capacity, environmental protection, and future scalability. A robust design starts with route selection, which should always prioritize simplicity and minimize length to reduce attenuation and potential interference. However, simplicity often conflicts with the realities of modern architectural spaces, such as those found above suspended ceilings or under raised access floors. In these interstitial spaces, the designer must account for physical support, ensuring that cables are not subjected to undue stress or crushing weight. This is where the discipline of our trade meets the messy reality of construction, requiring us to protect media from mechanical damage while maintaining accessibility for the inevitable moves, adds, and changes that define a life cycle of a network. One of the most frequent points of failure in cabling systems is an insufficient understanding of how physical pathways interact with electromagnetic interference. We must strictly maintain separation between our low-voltage media and potential EMI sources, which typically include electrical power lines, fluorescent lighting, and industrial machinery. The standard approach requires adherence to specific distance requirements, as defined by TIA standards, which vary based on the shielding of the cable and the voltage of the interfering source. Beyond EMI, we must respect the physical limitations of the cables themselves, specifically the minimum bend radius. If a cable is pulled too tightly around a tight corner, or if it is crushed by a poorly placed J-hook, the internal geometry of the pairs or the fiber strands can be permanently altered. This degradation of the physical layer often remains invisible during initial testing, but will manifest as intermittent signal loss under high-load conditions. Pathways must also account for future-proofing, which brings us to the crucial concept of the fill ratio. We utilize specific cross-sectional area formulas to determine the capacity of conduits, cable trays, and raceways, with a standard industry limit often enforced at 40% total capacity. This might seem inefficient to a casual observer, but it is a critical safety margin designed to prevent thermal bundling and structural strain on the cables at the bottom of a stack. When we fill a pathway beyond this limit, we restrict airflow, allowing heat to accumulate within the cable bundle and potentially degrading the performance of high-speed copper cabling. Furthermore, exceeding this capacity makes it physically impossible to add new lines in the future without damaging existing installations, thereby violating the fundamental principles of a scalable infrastructure design. The choice between continuous closed pathways, like rigid and EMT conduit, and open accessible pathways, such as cable trays and J-hooks, depends entirely on the unique requirements of the deployment environment. Closed pathways are mandatory, where physical security is paramount or where the environment contains hazardous debris or corrosive elements that could damage the cable sheath. Conversely, open pathways offer the visibility and accessibility necessary for high-density horizontal distribution, allowing for easier maintenance and modifications. J-hooks, which are perhaps the most common component in open cabling, must be sized and spaced appropriately to ensure they do not create stress points or violate the maximum sag requirements of the cable run. Each component, from the anchors in the ceiling slab to the protective sleeves through firewall penetrations, serves a specific structural purpose that, when calculated correctly, creates a resilient and stable backbone for the entire building. See you in the next lecture. Hello, welcome back. Today, we turn our attention to the engineered precision of conduit systems, specifically examining the mechanics of rigid and flexible pathways. In the world of ICT design, the conduit is not merely a pipe. It is a controlled environment for your cabling media. When we select between EMT, RMC, or PVC, we are essentially defining the physical limits of our distribution system. The fundamental rule for any conduit system is the management of the cross-sectional fill ratio. TIA standards typically dictate a 40% fill limit for a conduit with 2 or more cables, while a single cable is restricted to 53% and 2 cables to 31%. These percentages are not arbitrary. They exist to prevent mechanical stress and to ensure that the internal heat generated by the cables is properly dissipated. When you calculate fill, you must take the outer diameter of every cable, square it, and then determine the aggregate area occupied. Failure to respect these ratios leads to difficult pulls, potential jacket damage, and non-compliance with the NEC. Managing the trajectory of a conduit run requires strict adherence to geometric constraints. The standard limitation is a maximum of 180 degrees of cumulative bends between pull points, which usually translates to 2 90-degree bends or equivalent sweeps. If your pathway exceeds this, you are significantly increasing the pulling tension and the risk of sidewall pressure exceeding the cable's rating. For optical fiber, the sweep radius is particularly critical because fiber is fragile. Sharp bends can result in macro bending losses and permanent attenuation. Copper bundles, while more robust, are prone to elongation if they are forced around too many obstacles. Therefore, the implementation of conduit bodies like LBs, LLs, and LRs is not just about getting around a corner. These fittings facilitate easier cable transition, provided the internal dimensions of the body are designed to accommodate the bend radius of the specific media being installed. When architectural obstacles force a nonlinear path, we introduce offsets, kicks, and saddles to bypass structural elements. Each of these physical deviations adds to the total pulling tension, which is essentially the force required to slide the cable through the raceway. You must calculate this tension by considering the coefficient of friction between the cable jacket and the conduit wall. This is exactly where specialized cable pulling lubricants become mandatory. These substances lower the coefficient of friction, acting as a microscopic buffer. Without adequate lubrication, you risk catastrophic jacket tearing, which renders the cable useless in terms of fire ratings and signal integrity. Furthermore, we must monitor sidewall pressure to prevent the crushing of the internal twisted pairs or the fracture of fiber strands during the installation process itself. Physical security of the pathway infrastructure is the final but equally vital aspect of our design discipline. A closed pathway system must be robust enough to prevent unauthorized physical access to the media within. This means ensure that all conduit terminations are properly bushed to prevent abrasion, and that pull boxes are correctly sized not only for the volume of cable, but for the physical manipulation of the bundle. When we design these systems, we are building a foundation that must remain defensible for decades. Every calculation regarding fill, every decision to use a certain radius, and every choice of conduit material contributes to a resilient and scalable distribution network. Mastery of these physical parameters ensures that your designs meet the professional standards demanded of an RCDD candidate. I will see you in the next lecture. Welcome back to our exploration of high-capacity pathway infrastructures. In this session, we will examine the technical requirements and design considerations for cable trays and surface raceway systems. When we approach the design of high-density telecommunication spaces, cable trays serve as the structural backbone for horizontal distribution. These systems are categorized primarily by construction type, including ladder trays, ventilated troughs, solid bottom designs, and wire mesh basket trays. Ladder trays are frequently chosen for heavy-duty applications where maximum airflow is required to prevent thermal buildup within large cable bundles. In contrast, wire mesh basket systems offer superior flexibility for complex routing requirements in constrained ceiling plenums or underfloor spaces. Regardless of the type chosen, you must adhere to strict structural load specifications, ensuring that the tray can support the cumulative weight of the cables plus the necessary safety factors without exceeding the manufacturer's deflection limits. The distance between supports is a critical variable, as excessive span lengths lead to sagging, which can cause detrimental stress on cable jackets and internal geometry. Supporting these systems requires a disciplined approach to mechanical hardware selection, such as trapeze hangers, center-hung brackets, or wall-mounted cantilever supports. Each method introduces different stress profiles on the structural ceiling or wall, and you must verify that the building substrate can accommodate these loads. When calculating the capacity of a tray, we look at the volumetric fill ratio, which dictates how much of the cross-sectional area is occupied by cables. For data centers and equipment rooms, this is not just about fitting as many cables as possible into a space. It is about maintaining the thermal dissipation characteristics. Power over Ethernet, or PoE, introduces significant heat during operation, and if cables are bundled too tightly, the heat cannot escape effectively, leading to unwanted attenuation or even long-term damage to the link. You should always reference the manufacturer's fill guidelines and derating tables to ensure that your design remains within acceptable thermal thresholds. Managing cable transitions within a tray system requires meticulous planning to protect the physical integrity of the transmission media. Every change in elevation or direction imposes stress that can impact the minimum bend radius of your copper or fiber optic cables. If you encounter a vertical drop, you should implement waterfall components or dropouts to ensure the cable is supported throughout the transition rather than kinked over a sharp tray edge. Radius limiters are equally essential at horizontal intersections to prevent the cable from catching or bending beyond its rated limit. Think of these transitions as the joints in the cabling infrastructure. If they are improperly designed, they become the primary points of failure for the entire system. By standardizing the use of radius-controlled fittings, you guarantee that even the most dense horizontal distribution remains compliant with TIA standards throughout the life cycle of the facility. A frequently overlooked aspect of metallic cable tray design is the requirement for electrical continuity and equipotential bonding. Because these trays are made of conductive materials, they must be treated as part of the facility's grounding and bonding framework to protect personnel and equipment from electrical faults. You must ensure that every segment of the tray is mechanically connected to the next using specific bonding jumpers that bridge the splice plates, as these connections are often high resistance despite appearing secure. Furthermore, you must attach these trays to the telecommunications main grounding bus bar or the appropriate telecommunications grounding bus bar using listed grounding clamps and copper conductors sized according to the National Electrical Code. Failure to maintain electrical continuity throughout the entire tray run essentially creates an ungrounded metallic structure, which is a significant safety hazard in the event of a power surge or a fault in nearby equipment. This grounding effort serves as a path of least resistance for potential fault currents, allowing overcurrent protection devices to clear faults rapidly and preventing hazardous touch voltages from persisting on the cable management infrastructure itself. See you in the next lecture. Welcome back to this exploration of structured cabling infrastructure. In this session, we examine the technical requirements for creating pathways through solid building components, specifically through core drills and installed sleeves. When we transition from a telecommunications room into the broader building environment, we frequently encounter concrete decks and masonry walls that act as structural barriers. The process of penetrating these elements requires a disciplined approach, as the structural integrity of the facility must remain uncompromised throughout our installation. Before any mechanical action occurs, one must verify the composition of the barrier, particularly with concrete structures that utilize post-tension cables. Severing a post-tension tendon is a catastrophic failure that can cause localized or total collapse of the structural span. To mitigate this risk, industry professionals utilize ground-penetrating radar or radiographic X-ray scanning to map the internal density and identify the exact locations of rebar, conduits, and tendons. Never assume that a blueprint accurately reflects the as-built reality of hidden structural members, as minor floor-level adjustments during original construction can shift these components significantly. Once we have confirmed the safety of a location, the installation of a sleeve becomes our primary method for maintaining an organized and protected pathway. An electrical metallic tubing or EMT sleeve is typically employed to provide a smooth, durable conduit through the wall or floor. When placing these sleeves in floor assemblies, we must intentionally extend the conduit above the finished floor, often abbreviated as AFF, to a specific height. This elevation is not an aesthetic choice, but a protective measure designed to prevent water ingress from surface cleaning or accidental spills from infiltrating the pathway and damaging the enclosed cabling. Furthermore, any metal sleeve presents a potential hazard due to its sharp edges, which can easily strip the sheath from a fiber optic cable or nick the insulation of copper pairs. We address this by installing protective bushings on both ends of the sleeve, ensuring that the transition into and out of the wall is smooth and does not introduce mechanical stress to the media. Moving beyond simple circular penetrations, we occasionally face the need to route high-capacity pathways like cable trays through fire-rated walls. This requirement necessitates the design and installation of slot penetrations, which are considerably more complex than standard core drills. When we cut a large rectangular opening for a tray, we create a significant void that fundamentally alters the load-bearing characteristics of the wall or slab. To regain the necessary structural capacity, we must integrate reinforcement members, such as steel lintels, to distribute the load around the perimeter of the opening. The spatial geometry of these slots must be calculated with precision to maintain the continuity of the tray system, while ensuring that there is sufficient room remaining for code-compliant fire-stopping materials. We are not merely creating a hole, we are re-engineering a small section of the building envelope to facilitate technology while protecting the life safety rating of the structure. The fire-resistive rating of the building is perhaps the most critical constraint in our planning phase, as any breach must be restored to its original performance level. When we pass cables through a core-drilled or sleeved opening, the remaining void creates a chimney effect that allows smoke and flames to bypass fire-resistant barriers during an emergency. It is a fundamental obligation of the designer and the installer to ensure that each penetration is properly sealed after installation using listed systems. These systems are tested to resist fire for specific durations, and the combination of the sleeve, the cable, and the sealant must match the requirements of the building code. If we fail to account for the thickness of the barrier or the heat transfer properties of the metallic sleeve, we risk creating a single point of failure that compromises the safety of the entire floor. Achieving technical proficiency in this area requires a balance between mechanical requirements, strict adherence to structural norms, and an uncompromising commitment to fire safety standards. I will see you in the next lecture. Welcome back to our exploration of telecommunications infrastructure design. In this session, we investigate the precise methodologies required for calculating and selecting fire-stopping systems to ensure life safety in pathway penetrations. Fire stopping is not merely a task of sealing a hole, it is a critical engineering function that preserves the fire rating of a structural assembly. When we penetrate a fire-rated wall or floor to install conduits or cable trays, we create a breach that fire, smoke, and toxic gases can exploit. The primary objective is to restore the barrier's integrity to match or exceed its original hourly rating. To achieve this, practitioners must understand the interaction between the barrier material, which could be concrete, gypsum, or wood, and the penetrant, such as cable bundles or metallic conduits. We rely on standardized testing protocols, specifically ASTM E814 and UL 1479, to define the performance criteria. These standards provide a consistent framework for measuring how well a material holds against the hazards of a combustion event. Without this rigorous oversight, a pathway serves as a chimney, accelerating the spread of a fire throughout a building. Understanding the material science behind fire stopping is paramount for any designer. We classify these materials based on their physical reaction to heat, such as intumescent, endothermic, or ablative properties. Intumescent materials are particularly interesting because they expand when exposed to fire. effectively closing off openings and sealing gaps created by melting cable jackets. Endothermic materials absorb heat through chemical reactions to cool the penetrants, while ablative materials form a crust that resists flame erosion. When dealing with combustible penetrants, like plastic conduit or insulated copper cables, intumescent properties are usually required to compensate for the volume lost as the penetrant incinerates. For non-combustible penetrants like steel conduit, the focus shifts toward preventing thermal conduction and smoke leakage. Choosing the incorrect material classification can result in catastrophic failure during a real-world fire incident. The UL Fire Resistance Directory serves as our primary reference for selecting verified systems. Within this directory, we encounter specific ratings that guide our design choices. The F rating represents the duration in hours that the system prevents flame passage. We also look for the T rating, which indicates the time before the temperature on the non-fire side exceeds 325 degrees Fahrenheit above the ambient temperature. Smoke leakage is critical for life safety, evaluated via the L rating, representing the amount of air leakage in cubic feet per minute per square foot. Furthermore, the W rating identifies a system's ability to resist water penetration, which is vital when addressing modern building code requirements for fire suppression system containment. Every combination of barrier type and penetrant requires a specific engineered system, and it is the designer's responsibility to find a tested assembly that matches their specific site conditions. Calculating the mechanical aspects of a Firestop installation requires careful attention to detail. We must determine the annular space, which is the gap between the penetrant and the edge of the opening. This space must be wide enough to accommodate the Firestop material, but narrow enough to remain within the tested parameters of the selected UL system. Volumetric fill ratios are particularly important when using Firestop putties or pillows to ensure that we do not overload a sleeve, which could impede the expansion of intumescent materials. If a mechanical transit system is used, we must verify the internal dimensions and the seal pressure against the cable bundle diameter. Relying on vague estimations is insufficient. One must verify the specific installation manual for every product to ensure the volume of material provided is sufficient for the diameter and quantity of cables penetrating the barrier. Engineered systems provide a structured approach to documentation and compliance. By carefully documenting the wall or floor type, the specific penetrants, and the hourly rating required by local codes, we finalize the design in a way that is easily auditable by inspectors. This documentation must explicitly list the chosen UL system, certifying that the configuration exists precisely as tested. If a specific condition does not appear in the UL directory, one must seek an engineering judgment from the manufacturer, which provides a technical assessment based on existing test data. This process ensures that every pathway in your design is protected by a proven mechanism, keeping the occupants safe and keeping the facility in compliance with national and local fire safety regulations. These calculations form the backbone of a robust life safety strategy within the telecommunications space. See you in the next lecture. Welcome back to another session where we will dive into the technical rigors of mechanical pathway support and structural load calculations. In this lesson, we will examine the critical engineering principles behind pathway load and structural support for telecommunications infrastructure. We will focus on calculating aggregate system weights and designing robust attachment methods to ensure long-term mechanical safety. When we approach the design of a pathway system, we must first account for the total static load imposed by the infrastructure. This involves summing the weight of the cable tray, the conduits, and the maximum design density of the copper or fiber optic cables themselves. It is a common mistake to calculate based on empty tray weight, yet real-world scenarios demand that we design for the maximum capacity of the pathway when it is fully populated. We must apply a factor of safety to these static loads, accounting for potential future cable pulls that could incrementally increase the load on the supports. Dynamic loads must also be considered, particularly in environments where machinery causes vibration or where seismic activity is a credible risk factor. A tray system that is secure under static conditions may fail if the fasteners are not rated to handle the lateral forces exerted during a seismic event. Calculating these forces requires a precise understanding of the weight distribution across the span of the trapeze or wall-mounted support. The choice of fastening hardware is not merely a matter of convenience. It is a fundamental engineering decision dictated by the base material properties. When fastening to concrete, we must distinguish between the tensile strength of the concrete and the pull-out strength of the specific anchor. A wedge anchor provides high load capacity in solid concrete, but it is entirely unsuitable for hollow masonry or lightweight block construction. In such cases, a toggle bolt or a specialized chemical anchor is required to distribute the load across a larger surface area inside the wall cavity. For steel structures, threaded rods combined with beam clamps are common, but we must ensure that the orientation of the clamp does not introduce a bending moment that could compromise the rod's structural integrity. Each fastener has a manufacturer-verified shear and tensile limit, and the designer must ensure that the total load experienced by any single point of attachment never exceeds these thresholds. Never rely on friction-based fasteners alone if there is any chance of significant vibration or dynamic shock, as these can loosen over time and lead to a catastrophic failure of the entire pathway assembly. Designing a trapeze support system using unistrut and threaded rods requires a methodical approach to geometry and load rating. The threaded rod, which acts as the primary tension member, represents the bottleneck of the mechanical connection between the ceiling and the cable tray. We calculate the maximum allowable tensile load of the rod based on its diameter and material grade, typically using standard steel rods that provide a high margin for structural safety. If we have a long span of tray supported by a trapeze, we must verify that the horizontal channel, or unistrut, can span the distance without exceeding its allowable deflection limit. Excessive deflection is not just an aesthetic issue. It can cause the tray to sag, creating points of high friction where cables could be damaged during installation. Furthermore, the connection between the threaded rod and the trapeze channel must be reinforced to prevent the rod from pulling through the channel slot under heavy loads. By documenting these calculations, the designer creates a verifiable audit trail that proves the mechanical resilience of the installation under both normal use and environmental stressors. See you in the next lecture. Welcome back. Today we examine the fundamental physical sciences and electromagnetic properties that govern the performance of copper telecommunications cabling. When we transmit data over copper, we must first understand how twisted pair architecture manages electromagnetic fields. The reason we use balanced twisted pairs is to exploit the principle of common mode rejection, where the equal and opposite signal polarities cancel out noise induced by the surrounding environment. By varying the lay lengths, the distance required for a complete 360-degree twist across different pairs within the same jacket, we prevent pairs from coupling and creating signal bleed. These precise twist rates are what allow us to mitigate both electromagnetic interference and radio frequency interference in high-density environments. If these twists were uniform across all pairs, the capacitive coupling would lead to significant performance degradation. Understanding the physics of this cancellation is the bedrock upon which all certified cabling performance rests. Moving from geometry to electrical characteristics, we must look at the variables that physically limit a cable's ability to carry a signal. Resistance is the primary antagonist here, defined by the cross-sectional area of the conductor, typically measured in American wire gauge sizing, and the material properties of the copper itself. As the signal travels, it also suffers from attenuation, which is a logarithmic loss of signal strength caused by both resistance and dielectric heating within the insulation. Capacitance further complicates this by essentially creating a storage effect that filters out higher frequency components of our digital pulses. When we add inductance to the mix, we arrive at the characteristic impedance, which must be kept constant at 100 ohms to prevent signal reflections that cause return loss. Every change in the structural composition of the cable, such as kinks in the jacket or poor termination practices, creates an impedance mismatch that acts as a signal echo. High-frequency transmission brings unique challenges, particularly the skin effect, where current tends to flow only on the outer surface of the conductor. Because the effective cross-sectional area decreases as frequency increases, resistance effectively rises, exacerbating attenuation at the higher bandwidths required by modern standards. We also have to account for the impact of temperature, which increases the resistance of the copper, leading to the requirement for insertion loss derating in hot environments. When conductors are solid, they provide superior stability for permanent links, whereas stranded conductors offer the flexibility needed for patch cords at the cost of higher signal attenuation. The dielectric constant of the insulation material, such as polyethylene or fluorinated ethylene propylene, directly impacts the velocity of propagation, affecting the timing and potential skew between pairs. These physical traits dictate the upper bound of the bandwidth that a given channel can reliably support. Crosstalk represents the most significant barrier to achieving high-speed data rates, as it concerns the unintended transfer of energy between adjacent circuits. Near-end crosstalk, or next, occurs at the transmitter end and is the most disruptive because the signal here is at its strongest, making the interference signal proportionately louder. Far-end crosstalk, or FEXT, is measured at the receiver end, while alien crosstalk, or AXT, represents the interference bundled from adjacent cables in a pathway. We master these through the attenuation to crosstalk ratio, which mathematically defines the signal-to-noise margin required for a usable channel. If the attenuation is too high or the crosstalk is too severe, the receiver cannot distinguish between the data bits and the background noise. Balancing these factors is ultimately what determines whether a copper installation meets the stringent requirements for high-category performance. See you in the next lecture. Welcome back. Today we will navigate the technical specifications of balanced, twisted pair copper cabling and the rigorous standards governing their physical termination. When we discuss copper transmission, we must view the cable as a carefully engineered component where every twist and connector interface serves to preserve signal integrity against electromagnetic interference. The TIA 568 standard defines categories based on their electrical performance, which is fundamentally tied to the frequency bandwidth and the suppression of crosstalk. Category 5E is specified up to 100 MHz, providing enough headroom for 1G base T data transmission using all four pairs of the cable. As we move to Category 6, the standard pushes the boundary to 250 MHz, which necessitates stricter physical tolerances during manufacturing and installation to support stable high-speed performance. Category 6A represents a major leap, extending the frequency range to 500 MHz to facilitate 10 gigabits per second operation over the full 100-meter channel distance. Understanding these boundaries is not merely about memorizing numbers, it is about grasping why the attenuation to crosstalk ratio is the deciding factor in whether a system functions under the heavy load of modern multi-gigabit Ethernet traffic. Termination represents the most vulnerable point in a structured cabling channel because the physical structure of the twisted pairs is disturbed to make the connection. For 8P8C modular connectors, commonly referred to as RJ45, the primary design objective is to maintain the twist rate as close as possible to the point of contact. TIA standards dictate that the maximum allowable untwist for Category 5E is 1/2 inch, while Category 6 requires a more restrictive 1/4 inch limit to prevent significant impedance discontinuities. When dealing with IDC punch-down blocks like a 110, 66, or BI, the force applied during the punch process must be calibrated to penetrate the insulation without damaging the conductor itself. If you exceed the maximum untwist distance, the localized signal reflections known as return loss will degrade the link performance significantly. This is particularly critical in systems supporting power over Ethernet, where excessive resistance at an improperly terminated contact can lead to localized heating and potential hardware damage under high current loads. Distinguishing between shielding strategies requires a sober assessment of the environment, as shielding is often misunderstood as a panacea for poor installation practices. Unshielded twisted pair, or UTP, relies on the balanced differential signal and precisely maintained twist to mitigate interference, which is sufficient for most office environments. However, in industrial spaces or areas with high electromagnetic interference, moving to FUTP or S/FTP becomes a structural necessity. These constructions involve a foiled or braided shield that must be properly bonded to the grounding system through a high-quality 360-degree shield termination. If the shield is not connected to a common ground reference at the telecommunications bonding backbone, it can act as a giant antenna, capturing common mode noise instead of blocking it. Furthermore, poor grounding creates the risk of ground loops, where multiple potential gradients induce current flow through the shielding, inadvertently creating more noise than the shield was meant to block in the first place. As we look toward the future of high-density PoE and multi-gigabit deployments, the physical copper infrastructure demands a level of precision that marginalizes legacy installation habits. Your role as an RCDD involves specifying the correct media and termination hardware that provides the necessary headroom for the intended application during the entire life cycle of the building. We are past the era where a simple continuity check was sufficient for certification, as modern standards require comprehensive testing of next, fixed, and return loss parameters to ensure the cabling can handle complex signal profiles. Every decision regarding cable categorization, jacket rating for fire safety, and termination density directly impacts the system's ability to facilitate uninterrupted data and power delivery. By mastering these foundational aspects of copper physics and termination, you ensure that the physical layer remains a robust, reliable, and invisible servant to the high-performance network applications it supports. I will see you in the next session. Welcome back to our technical journey through the infrastructure of modern communication networks. In this lesson, we will focus on the fundamental physical and optical principles that define fiber optic transmission and cable construction. To understand fiber optics, we must first look at how light interacts with matter through the lens of geometric optics. The core of an optical fiber is a silica glass strand designed to guide light via total internal reflection, a phenomenon that occurs when light travels from a medium with a higher refractive index to one with a lower refractive index. Snell's law provides the mathematical framework for this, describing how the angle of refraction changes based on the refractive indices of the core and the cladding. The numerical aperture, or NA, effectively dictates the light-gathering capability of the fiber, representing the range of angles at which light can enter the fiber and be successfully transmitted. If a light ray enters at an angle exceeding the acceptance cone defined by the NA, it will not undergo total internal reflection and will instead be lost into the cladding. This interaction is the bedrock of fiber performance, as the refractive index profile determines whether we are dealing with step index or graded index fibers. Graded index profiles in particular are essential in multimode fiber to reduce modal dispersion by causing light rays traveling longer paths to move at higher velocities. Once we grasp the light path, we must consider how the physical cable protects that delicate glass journey through various environments. The basic fiber structure consists of the core, the cladding, and a primary coating, which is typically the first layer of acrylate applied during the drawing process to protect the glass from moisture and microscopic surface defects. Beyond the coating, we find the buffer, which can be categorized as either tight buffered or loose tube depending on the intended application. Tight buffered designs are generally used for indoor cabling, where the fiber is in direct contact with the buffer, offering ease of termination and mechanical robustness for patch cords. In contrast, loose tube cabling features fibers floating within gel-filled or dry water-blocked tubes, which provides excellent protection against thermal expansion and mechanical stress in outdoor environments. To ensure the cable can withstand pulling forces during installation, manufacturers incorporate strength members like aramid yarn, popularly known by the trade name Kevlar, which provide high tensile strength without adding significant weight or bulk. Signal integrity relies on matching the appropriate wavelengths to the physical medium while mitigating various sources of attenuation. We primarily operate in the infrared spectrum, with 850 nanometers and TEDScene 300 nanometers being standard for multimode systems, while single-mode applications leverage the 1310 nanometers and 1550 nanometers windows to minimize loss over long distances. Attenuation occurs due to both intrinsic factors, such as Rayleigh scattering caused by density fluctuations in the glass and infrared absorption caused by lattice vibrations, and extrinsic factors related to implementation. Microbending refers to small-scale deviations in the fiber axis caused by manufacturing defects or physical pressure, while macrobending occurs when the cable is bent beyond its minimum bend radius, allowing light to leak out of the core into the cladding. As engineers, we must calculate the total link loss based on these specific phenomena to ensure that the optical budget is sufficient to maintain the signal-to-noise ratio required by the active hardware at both ends. Poor understanding of these physics often leads to intermittent connectivity issues that are notoriously difficult to troubleshoot in the field. Deployment environments demand specific cable constructions that balance mechanical survivability with environmental resistance. For indoor plenum spaces, we must utilize cabling with flame-retardant outer jackets that meet strict smoke and fire spread requirements, often necessitating specialized materials. Outdoor deployments frequently employ armored jackets to protect against rodent damage and environmental elements, or central tube configurations that organize a high density of fibers in a compact footprint. Ribbon fiber constructions allow for mass fusion splicing, which significantly reduces the time required for high-count cable termination, though it necessitates careful management of the ribbon grouping. When selecting a cable, you must evaluate the thermal expansion coefficients, moisture exposure, and mechanical load-bearing requirements of the installation route to ensure long-term reliability. A failure to account for these specific deployment nuances can lead to premature degradation, nullifying the efficiency gains provided by the optical medium itself. See you in the next lecture. Welcome back. In this lesson, we will examine the physical and operational distinctions between single-mode and multi-mode optical fibers to refine your engineering design choices. To understand the core difference between these two technologies, we must look at the geometry of the fiber itself. Single-mode fiber, identified by ITUT standards such as G652, typically features a core diameter of approximately 9 microns surrounded by a 125-micron cladding. This extremely small core size forces light to travel in a single axial mode, which effectively eliminates the phenomenon known as modal dispersion. Because the light source does not bounce off the core cladding interface in multiple ways, the signal remains coherent over much longer distances. You will find that single-mode fiber, categorized by OS1 and OS2 standards, is the prerequisite choice for long-haul telecommunications and campus-wide backbones, where geographical reach and data integrity are non-negotiable. Multimode fiber, by contrast, utilizes larger core diameters of 50 or 62.5 microns, maintaining that same 125-micron outer cladding dimension. The larger core allows for multiple modes of light to propagate simultaneously, which introduces the significant engineering constraint of modal dispersion. As light rays travel at different angles and speeds through the core, they arrive at the receiver at slightly different times, which eventually causes signal degradation that limits both bandwidth and distance. The industry classifies these fibers as OM1 through OM5, with current designs favoring laser-optimized 50-micron fibers like OM3, OM4, and OM5 for use with high-speed vertical cavity surface emitting lasers. When you evaluate these, you must look closely at metrics like overfilled launch bandwidth and effective modal bandwidth, as these dictate the capacity for specific transmission rates in data center environments. When you are acting as an RCDD, your design methodology relies on balancing the physical properties of the fiber with the requirements of the active equipment on either end of the link. Multimode fiber is generally cheaper to deploy because the larger core diameter makes it easier to couple light from relatively inexpensive LED or VCSEL transceivers. However, the bandwidth limitations imposed by modal dispersion mean that multimode fiber is largely relegated to enterprise data centers and short-reach backbone connections within a single building. If your design requires a link spanning multiple buildings or extreme bandwidth requirements that exceed the capabilities of laser-optimized multimode glass, you must pivot to single-mode solutions. Single-mode systems are limited primarily by chromatic dispersion in the power output of the transmitter rather than the physical dispersion of the signal itself, allowing for nearly limitless future-proofing. Deciding between these media types requires a cold assessment of the budget and the physical environment of the installation. A data center environment typically benefits from the lower transceiver costs associated with multimode OM4 or OM5, provided the link lengths stay within the standardized ranges for the desired protocol speeds. Conversely, if you are designing a campus backbone that traverses several hundred meters, the higher cost of single-mode transceivers is offset by the longevity of the infrastructure and the ability to upgrade transmission electronics without replacing the underlying fiber. You must also consider the future scalability of the system. Single-mode fiber provides a practically infinite runway for higher data rates as optical technology progresses. While the transceiver components may carry a premium today, the cost is often eclipsed by the disruption and expense of future physical cable plant upgrades. Ultimately, the choice comes down to the fundamental physics of light propagation versus the realities of current project economics. By mastering the distinction between the 9-micron single-mode core and the larger multi-mode geometries, you gain the ability to specify the right tool for the job. You will encounter situations where a hybrid approach, using single-mode for external runs and multi-mode for short-distance server-to-switch connectivity, is the most professional and cost-effective layout. Approach these decisions by verifying the link budget against the manufacturer-specified loss and bandwidth metrics, rather than relying on generalized rules of thumb. Your responsibility is to ensure that the physical layer of the network remains robust, capable, and aligned with international standards while respecting the constraints of the client's deployment scenario. See you in the next lecture. Welcome back. In this chapter, we will explore the precise techniques and hardware required for successfully splicing and terminating fiber optic cables in modern distribution networks. When we talk about splicing, we are essentially managing the continuity of light through glass fibers. The gold standard for permanent connections is fusion splicing, a process that utilizes an electric arc to melt the fiber tips together. To achieve a splice loss as low as 0.01 dB, the machine must perform intricate alignment of the fiber cores. Modern fusion splicers use either PAS, which stands for Profile Alignment Systems, or light injection and detection to align the fibers. Core alignment is significantly more accurate than cladding alignment because it compensates for core-to-cladding eccentricity within the fiber geometry. Before any arc is applied, the fiber must be stripped, cleaned, and cleaved with surgical precision. A poor cleave, even if microscopic, will deviate the end angle, preventing the cores from fusing correctly and causing unacceptable back reflection. Mechanical splicing is a different beast entirely, as it relies on physical alignment and index matching gel, rather than a permanent fusion of glass. The gel is engineered to have a refractive index close to that of the fiber core, which minimizes the signal reflection that occurs when light hits the air gap between two fiber ends. While mechanical splices are faster to install in the field during emergencies, they are vulnerable to gel degradation over time and environmental fluctuations. Many legacy environments still utilize mechanical methods, but their performance in terms of return loss often trails behind what fusion splicing can provide. When you are designing or auditing these systems, you must assess whether the environment justifies the convenience of a mechanical splice or demands the structural integrity of a fusion splice. Always consider the long-term maintenance implications when selecting the method for your installation. Turning to terminations, we encounter a wide array of optical connector form factors, each serving specific density and mechanical requirements. Common standards like the SC, LC, and ST connectors have defined the landscape for years, but the rise of high-density data centers has made MPO and MTP connectors indispensable. These multi-fiber connectors allow for rapid deployment by consolidating multiple fiber strands into a single interface, significantly reducing the space required in distribution frames. Beyond the physical shape, the polish type of the connector face determines the signal performance. The UPC, or ultra-physical contact, polish provides excellent return loss, but the APC, or angled physical contact, polish takes reflection management further. By angling the end face at 8 degrees, the APC connector ensures that reflected light is directed into the cladding rather than back down the fiber toward the source. Reliable optical performance is fundamentally a matter of hygiene and adherence to geometry standards like IEC 61300-3-35. Even the best splicing hardware will fail to meet loss budgets if the end face is contaminated with dust or oils. You must treat every connector interface as a potential failure point, requiring systematic inspection with a fiber microscope before mating. The termination process itself varies between methods, ranging from field-applied epoxy polish connectors to pre-polished splice-on connectors and simple pigtail splicing. When working inside splice closures or high-density fiber distribution panels, organization is the primary defense against future stress-induced failures. Tight bend radii and excessive tension are the enemies of optical clarity, and they will invariably inflate your insertion loss measurements during the final testing phase. See you in the next lecture. Welcome back to our journey through the technical requirements of modern cabling design. We are now moving into the specific mathematical rigor required to validate optical signal transmission performance. When we talk about a fiber link loss budget, we are essentially performing a predictive audit of the physical layer's integrity. The goal is to determine if your hardware, with its specific attenuation characteristics, can successfully transmit a signal from the transmitter to the receiver without dropping below the sensitivity threshold of your active equipment. We start by establishing the total allowable attenuation for the entire channel, which is the difference between the launch power of the light source and the minimum received sensitivity of the optical transceiver. This calculation must account for the specific attenuation coefficient of the fiber, which varies significantly depending on the wavelength employed. Multimode fiber at 850 nanometers typically exhibits an attenuation of 3.0 decibels per kilometer, while reaching 1300 nanometers brings that figure down to approximately 1.0 decibels per kilometer. Single-mode fiber is much more efficient, usually rated at 0.5 decibels per kilometer at 1310 nanometers and 0.4 decibels per kilometer at 1550 nanometers. By summing these values based on the physical distance of your cable run, you establish the baseline fiber loss before you even consider the hardware components. Beyond the inherent fiber attenuation, we must incorporate the discrete losses introduced by connections and splices along the pathway. According to TIA standards, a conservative estimation for a mated pair of connectors is 0.75 decibels, which serves as the worst-case design value. Fusion splices are significantly more efficient, and we should budget a maximum loss of 0.3 decibels per event to remain within acceptable margins. If your design includes 5 connectors and 2 fusion splices, your total hardware loss becomes a simple summation of these values added to your fiber attenuation. It is critical to calculate this budget for both the transmit and receive directions, as fiber properties are rarely perfectly symmetrical across a diverse plant infrastructure. Maintaining a power margin, typically of 2 to 3 decibels, is professional practice to account for future repairs, cable movement, or the natural degradation of laser diodes over several years of operation. If your pre-calculated loss exceeds the equipment's power budget, you must reconsider the component selection or shorten the physical distance between your telecommunications rooms. Testing protocols provide the empirical proof that our mathematical models reflect the physical reality of the installed plant. Tier 1 testing, utilizing an optical power meter and a stabilized light source, validates the total end-to-end loss of the link compared to the limit we calculated earlier. This is the absolute minimum requirement for certification, ensuring that the link is functionally capable of carrying the intended signal weight. However, Tier 2 testing employs optical time domain reflectometry, or OTDR, to provide a granular map of the entire fiber length. This is where we identify specific fault events, such as excessive reflection from a dirty connector or a sudden drop caused by a macro bend. An OTDR sends a pulse of light down the fiber and measures the backscatter, which allows us to visualize the physical characteristics along the entire span from the head end. Effective OTDR analysis requires the user to precisely configure the test set, starting with the index of refraction, which must match the fiberglass manufacturing specifications to ensure accurate distance measurements. We must also carefully select the pulse width, too short, and we lack the dynamic range to reach the end of the cable, but too long, and we increase the dead zone, obscuring events that occur close together. The dead zone is the region where the instrument is blinded by the high-intensity reflection of a connector, preventing the detection of a secondary event immediately following it. Ghost reflections are another common nuisance in traces, characterized by uniform, spaced pings that appear like connectors in the middle of a fiber span. These are actually multiple reflections occurring between 2 highly reflective connections that have not been properly cleaned or indexed. When you see an event that does not correspond to a known patch panel or splice, you must verify the index of refraction and check for mechanical stress on the cable that could be inducing a bend. Post-deployment troubleshooting hinges on our ability to distinguish between actual cable faults and misconfigured test equipment. If your trace shows a high-loss event, check the macro bend signature, which will manifest as high attenuation at 1550 nanometers, but significantly less at 1310 nanometers. This wavelength dependency is the telltale sign of a fiber bend that is physically stressing the core rather than a compromised splice. Conversely, a fusion splice event that exceeds our 0.3 decibel design threshold is usually indicative of a clean room failure or poor alignment during the splicing process. By mathematically defining our loss budgets before the first pull and validating them with documented Tier 2 traces, we create a record of performance that protects the design intent. This process of systematic verification ensures that the physical layer is not just a collection of glass and plastic, but an engineered foundation for high-speed data transmission. See you in the next section. Welcome to this section on bonding and grounding. where we will establish the mandatory safety principles for protecting both human life and sensitive infrastructure. You will learn the critical engineering requirements for managing electrical potentials within modern telecommunications facilities. In any complex building infrastructure, the distinction between grounding and bonding remains a point of persistent confusion, yet it is arguably the most vital concept in electrical safety. Grounding, in its strictest sense, refers to the intentional connection of a circuit or device to the earth, typically through a grounding electrode system. This earth connection serves as a reference point for voltage and provides a dedicated path for the dissipation of lightning surges or unintentional contact with live power lines. Bonding, by contrast, is the process of interconnecting all metallic components in a facility to create an electrically continuous path. The goal here is not necessarily to reach an earth potential at every point, but rather to ensure that all metallic parts are at the same equivalent potential. When you interconnect racks, cable trays, and conduit, you effectively eliminate potential differences between them, which prevents the dangerous flow of current through anyone who might touch two metallic objects simultaneously. Understanding the behavior of fault currents is essential for any designer, as current always seeks to return to its source, not the earth. When a short circuit occurs, the fault current flows through the equipment grounding conductor back to the overcurrent protection device, which triggers the breaker to trip and de-energize the circuit. This fault-clearing process relies entirely on the impedance of the path. If the path has too much resistance, the current may not reach a level high enough to trip the breaker, leaving the circuit energized and dangerous. This is where the physical characteristics of conductors come into play, specifically concerning the skin effect. At high frequencies, such as those found in lightning strikes, current tends to travel along the outer surface of a conductor rather than its core. Consequently, flat braided straps are often superior to round conductors in these scenarios because they offer a larger surface area relative to their cross-section, effectively lowering the impedance for transient surges. When we construct these bonding systems, the quality of our connections determines the long-term reliability of the entire protection scheme. You must prioritize the use of exothermic welding, commonly known by the brand name CAD-weld, for critical connections, particularly those involving the grounding electrode system. An exothermic weld uses a chemical reaction to fuse metal components together at a molecular level, creating a permanent connection that will not loosen or corrode over time. While irreversible compression fittings are also acceptable and highly reliable when installed with the correct tooling, they do not offer the same structural integrity as a molecularly fused bond. A common design failure is relying on mechanical lugs that can vibrate loose or oxidize, leading to a high-impedance connection that might fail exactly when you need it most. By mandating low-impedance paths that are structurally sound, we ensure that catastrophic electrical energy is directed away from our sensitive ICT hardware rather than through it. The telecommunications bonding infrastructure acts as an extension of the AC system, specifically tailored to the needs of IT hardware. While the AC equipment ground ensures the circuit breaker functions during a fault, the telecom-specific bonding system addresses noise reduction and potential equalization across the distribution backbone. You should view the telecommunications main grounding busbar as the central hub for this specialized system, effectively tying all rack-mounted equipment to the building's main grounding electrode. When you design these systems, avoid creating circumstances that allow for ground loops, which occur when multiple paths to ground exist that have different potentials. A system burdened by ground loops can introduce unwanted hum and data corruption into sensitive telecommunications circuits, often manifesting as intermittent packet loss or interface resets. Effectively managing these potentials requires a methodical approach to how you connect your shieldings, metallic supports, and chassis grounds to the dedicated bus bars. See you in the next lecture. Welcome back. Let's get into the specifics of telecommunications grounding infrastructure and how the ANSI TIA 607 standard defines the backbone. The Telecommunications Main Grounding Busbar, or TMGB, functions as the dedicated extension of the building's electrical service ground to the telecommunications infrastructure. Its primary purpose as a central attachment point is to consolidate all bonding conductors within a facility to ensure a common potential across the system, effectively mitigating ground loops and transient voltage surges. You must position the TMGB within the main telecommunications room or entrance facility, situated near the building's electrical service grounding electrode. The bus bar itself is typically a pre-drilled copper bar with a thickness of at least 6 millimeters and a width of 100 millimeters, though length varies based on the number of required connections. When installing this component, you are required to use appropriate insulators to isolate the bar from the supporting structure unless the design specifically calls for otherwise. Every connection to the TMGB should employ two-hole compression lugs, which provide superior mechanical stability and lower contact resistance compared to single-hole solutions. Before attaching the lugs, it is imperative to apply an antioxidant joint compound to the contact surfaces to prevent oxidation and ensure the longevity of the electrical bond. This attention to detail prevents galvanic corrosion, which is a silent killer of grounding integrity in high humidity environments. Moving away from the entrance, we encounter the Telecommunications Grounding Busbar, or TGB, which acts as the localized grounding hub inside each individual telecommunications room. While the TMGB is the master, TGBs are the satellites that facilitate local bonding for racks, cabinets, and ladder racks within their respective spaces. The TGB is connected directly back to the TMGB via the telecommunications bonding backbone, a conductor which I will elaborate on shortly. Effectively, the TGB provides a low-impedance path to ground for all information technology equipment housed within that room. When sizing these components, you should reflect on the total number of telecommunications equipment connections expected in the future, as bus bars are difficult to upgrade once the cabling infrastructure is fully populated. It is common practice to leave 20% of the holes on the TGB vacant to accommodate future expansion, preventing the need for disruptive retrofitting later. Placing the TGB adjacent to the primary copper or fiber backbone terminations creates a short, direct path, which is critical for minimizing impedance during fault conditions. Keep in mind that TGBs, like the TMGB, must be clearly identified and labeled to comply with safety standards and facilitate troubleshooting for maintenance personnel. The Telecommunications Bonding Backbone, or TBB, is the heavy-duty copper conductor that bridges the gap between the TMGB and all TGBs throughout the building. You calculate the size of this backbone conductor based on the linear distance it travels from the TMGB, which dictates the cross-sectional area needed to maintain voltage stability. Generally, for longer distances, the American wire gauge, or AWG, size must increase to compensate for the higher resistance of the copper path. For example, in many standard building configurations, typical TBB sizing requirements range from 6 AWG up to 3/0 or even 4/0 AWG for extensive spans in high-rise facilities. You must ensure that this conductor is stranded copper as it offers better vibration resistance and ease of installation compared to solid conductors. The TBB should be installed in a manner that avoids sharp bends, adhering to strict minimum bend radius limits for grounding wire to prevent mechanical stress that can lead to conductor work hardening. Because this backbone carries circulating currents during electrical faults, the physical routing must remain as straight as possible and avoid excess coils of wire, which would otherwise introduce unwanted inductance into the circuit. As we integrate the various metallic elements of the room into this grid, we must consider the bonding of equipment racks, cable trays, and building steel. You should treat every metallic section of a cable tray system as a continuous conductor by using bonding jumpers across every splice, ensuring that no mechanical joint relies solely on fasteners for electrical continuity. The grounding wire from a rack or cabinet connects directly to the nearest TGB using a dedicated bonding conductor, typically a 6 AWG green insulated copper wire. All attachments must use identified hardware, such as star washers or abrasive lug connections that penetrate paint and finishes to achieve solid metal-to-metal contact. If you are dealing with a multi-story building, the vertical runs of the TBB must be protected and properly supported within the telecommunications pathways, taking care to isolate them from signal-carrying cabling whenever feasible to prevent electromagnetic interference. This holistic approach creates a unified, low-impedance bonding grid that serves as the single reference point for the entire installation. By strictly following these parameters, you ensure that the structured cabling system remains protected against power surges, lightning, and equipment-level ground faults. I will see you in the next lecture. Welcome back. In this lesson, we will examine the technical mechanisms behind ground loops and the rigorous methodologies required to prevent their damaging effects. A ground loop occurs when two or more pieces of equipment are connected to the same signal path but reside at different ground potentials. In an ideal scenario, all points within a facility's grounding system share an identical voltage reference, essentially 0 volts relative to the earth. However, in reality, ground rods driven into different locations often exhibit varying potentials due to soil resistivity changes, distance from the main service entrance, or high impedance connections. When you connect two chassis using a metallic shield of a data cable, you effectively create a low impedance current path between these 2 points. Because the potential difference acts as a driving voltage, an unwanted common mode current begins to flow through the cable shield. This current is not part of the intended signal transmission and instead functions as a source of electromagnetic interference. Left unchecked, this phenomenon leads to degraded data integrity, intermittent cyclic redundancy check errors, and, in severe cases, the thermal destruction of communication transceiver components. The first line of defense against these circulating currents is the implementation of a coherent single-point grounding architecture. By ensuring that all equipment racks and cabinets ultimately reference a unified telecommunications main grounding busbar, we minimize the potential for voltage gradients between connected devices. This is further reinforced by the use of an equipotential bonding grid. Rather than relying on sporadic connections, a structured grid creates a low-impedance mesh that forces all metallic structures within the data space towards the same electrical potential. It is vital to understand that this is a strict requirement for high-availability environments. Furthermore, one must never rely on arbitrary metallic infrastructure, such as water pipes, as a substitute for a properly engineered telecommunications bonding backbone. Using plumbing for grounding is not only a violation of the National Electrical Code, but also introduces unpredictable earth paths that introduce new, uncontrollable loop potentials into the sensitive signal environment. When architectural constraints make a perfectly unified ground impractical, we must turn to isolation strategies to protect the equipment. Optical isolation, facilitated by fiber optic media converters, acts as the ultimate circuit breaker for ground loops. Because fiber optics transmit data via light rather than electrical pulses, the physical connection between pieces of equipment becomes fundamentally non-conductive. A fiber optic link effectively decouples the grounding domains of the two connected devices, rendering potential differences between them entirely irrelevant to the signal quality. For scenarios where copper remains unavoidable due to specific legacy interface requirements, isolation transformers can be employed to magnetically couple the signal while breaking the common electrical path. Choosing the correct strategy depends on the bandwidth requirements and the physical distance between your active network components and the power distribution panels. To verify the success of these design choices, technicians must employ precise diagnostic techniques during the commissioning phase. A clamp-on ground resistance tester is the industry standard tool for identifying active rogue currents within bonding conductors. By placing the CT clamp around a grounding wire, you can measure the actual current circulating through the system without disconnecting any hardware or interrupting live traffic. If you observe significant current flowing through conductors that are intended to be static references, you have likely identified a ground loop that requires immediate remediation. This process involves tracing the metallic path between the equipment and the grounding busbar to identify unintended multiple connections to earth. Maintaining a documented, verified path for all bonding conductors ensures that your distribution design remains within the strict parameters required for reliable, long-term operation of your signal infrastructure. I will see you in the next lecture. Welcome back. In this lecture, we examine the fundamental characteristics of alternating and direct current systems as they apply to telecommunications infrastructure. To understand the core of power distribution, we must start with the distinction between the electricity delivered to the building and the current utilized by the active equipment. Alternating current is the standard for utility power, characterized by its sinusoidal waveform where the direction of electron flow periodically reverses. Within the context of a telecommunications facility, we typically deal with three-phase power, which is chosen for its efficiency in delivering high loads to large-scale equipment environments. In a three-phase system, power is transmitted via three conductors carrying currents that are offset by 120 degrees, allowing for a constant power delivery that reduces the need for heavy neutral wire return paths in balanced scenarios. A critical concept here is the root mean square, or RMS voltage, which provides a meaningful measure of the effective voltage of an AC waveform relative to its peak value. When calculating the power delivered to an equipment rack, you must distinguish between real power measured in watts and apparent power measured in volt amperes. The ratio of these two values is the power factor, an essential metric that indicates how much of the energy being drawn is actually performing useful work versus being stored or lost as reactive power due to inductive or capacitive loads. Moving from utility AC to the internal environment of a central office requires an understanding of the rectification process. Telecommunications equipment, particularly switching infrastructure and optical line terminals, has historically relied on negative 48-volt direct current power plants. This standard exists because DC provides superior stability and allows for seamless integration with battery backup systems, ensuring that central offices remain operational during utility outages without the split-second gap inherent in some AC switching mechanisms. The conversion from AC grid power to DC is handled by rectifiers, which translate the utility's sine wave into a smooth, steady, unidirectional current. As a designer, you are responsible for calculating the total ampacity requirements to ensure that copper bus bars are sized correctly to prevent excessive voltage drop and thermal buildup. Sizing these bus bars is not merely about current carrying capacity, but also about managing the physical dimensions of the conductor to maintain efficiency and meet NEC clearance requirements. If our distribution architecture fails to account for the total load of the racks, the excess heat will degrade component life and potentially trigger circuit protection devices, leading to unnecessary downtime. When we integrate intelligent power distribution units into our racks, the complexity of load management increases significantly. Modern high-density compute environments often utilize redundant power feeds, designated as A and B, which are sourced from independent utility entrances or uninterruptible power supplies to ensure fault tolerance. You must calculate the load on each branch circuit carefully, ensuring that neither the A nor B feed exceeds the safe operating current of the distribution path. Especially when considering the inrush current of power supplies. The use of isolation transformers is another critical consideration, specifically for mitigating common mode noise and maintaining proper grounding references within sensitive digital circuits. A well-designed power infrastructure acknowledges that phase loading must be balanced across the three-phase distribution. Failure to perform this balancing leads to neutral current buildup, which can cause significant overheating in cables and transformers regardless of the total power being consumed. Every design choice, from the thickness of a bus bar to the selection of branch circuit breakers, must align with strict national electrical code regulations regarding service conditions and workplace safety. The precision of your capacity planning directly dictates the reliability of the entire network. If we overlook the physics of power factor correction or fail to identify the limitations of our rectifier stacks, we invite architectural vulnerabilities into the facility. Successful design requires a rigorous verification of all load calculations, ensuring that the infrastructure supports current demand while providing adequate headroom for future equipment additions without requiring a full rewiring of the power distribution chain. As you refine your approach to these power topologies, keep your focus on the intersection of theoretical electrical physics and the practical physical constraints of the workspace. By mastering these foundational elements, you provide the stability that high-density telecommunications loads demand in every installation you oversee. See you in the next lecture. Welcome back. In this lesson, we will examine the technical requirements for sizing uninterruptible power supply systems and emergency standby generators to maintain continuous operation. When we approach critical power redundancy, the primary objective is to build a buffer that bridges the gap between a utility failure and the stabilization of an alternate power source. An uninterruptible power supply, or UPS, acts as the immediate safeguard, providing clean, conditioned power while the generator climbs to its operational frequency and voltage. To size these systems correctly, you must aggregate the total volt-ampere load of all equipment connected to the critical power distribution units. It is not sufficient to simply sum the nameplate ratings, as this often leads to gross overestimation and inefficient system operation. Instead, you should focus on the steady-state power consumption while accounting for the maximum possible power factor of the connected load. A double conversion online UPS is the industry standard for mission-critical facilities because it isolates the load from raw utility power entirely, effectively creating a clean power environment regardless of input disturbances. Sizing battery systems requires a precise understanding of the load duration and the discharge characteristics of the chosen chemistry. Valve-regulated lead-acid batteries, or VRLA, are common due to their lower initial cost, but they are significantly heavier and require specific ventilation for hydrogen outgassing during charging cycles. Lithium-ion alternatives offer a much higher energy density and a smaller physical footprint, which is beneficial when floor load ratings are restricted. When calculating the required amp-hour rating, you must factor in the depth of discharge and the manufacturer's end-of-discharge voltage curves to ensure the runtime requirements are met under full load. Keep in mind that as VRLA batteries age, their internal resistance increases, which necessitates periodic capacity testing to ensure they can still deliver the required current during the final minutes of their rated runtime. Failure to account for these environmental and aging factors will almost certainly lead to an unexpected loss of systems during a prolonged outage. The integration of a standby generator introduces a different set of engineering constraints, specifically regarding fuel supply and mechanical startup time. The automatic transfer switch serves as the intelligent arbiter of power, sensing the loss of utility voltage and initiating the generator's cranking sequence. You must ensure that the UPS battery runtime is long enough to cover both the generator's startup delay and the stabilization period required for the ATS transition. Fuel storage sizing is typically dictated by the local jurisdiction's fire codes and the required operational duration, often measured in days or weeks rather than just hours. Furthermore, you should prioritize critical load panels so that the generator is not inadvertently tasked with supplying non-essential infrastructure like climate control for general office space during an emergency. The goal is to sustain only the systems that preserve life safety and maintain core data availability when utility power is absent. Designers must also be conscious of the physical infrastructure surrounding these power systems, particularly regarding weight distribution and thermal requirements. Large UPS cabinets and battery racks can exert high localized pressure on raised floor systems, requiring reinforced structural supports or specialized mounting frames. Ventilation is not merely a matter of comfort, it is a necessity for heat dissipation, as lead-acid batteries are highly sensitive to ambient temperature fluctuations that can shorten their design life significantly. If you place a UPS in a restricted space, you must provide sufficient airflow to prevent hotspots that lead to premature component failure. Every design choice, from the selection of the UPS topology down to the routing of the generator exhaust, involves a trade-off between reliability, efficiency, and maintenance accessibility. You are ultimately tasked with constructing a resilient power chain where no single point of failure can jeopardize the availability of the facility you are supporting. See you in the next lecture. Welcome back to our technical journey through the RCDD curriculum. In this session, we will examine the critical requirements for HVAC heat load calculations within high-density information and communications technology environments. Managing thermal density is perhaps the most significant constraint in modern data center design, where the concentration of active equipment often outpaces the cooling capacity of legacy infrastructure. When we design telecommunication spaces, we are essentially building precision thermal reactors that convert almost exclusive amounts of electrical energy into waste heat. Because the laws of thermodynamics are immutable, every watt of power consumed by a server, a power over Ethernet switch, or a persistent storage array must be rejected as heat. If the heat extraction rate equals the heat input rate, the equipment remains within its safe operating envelope. However, modern dense ICT spaces often experience heat densities exceeding the capabilities of ambient room cooling, which necessitates a shift from general conditioning to targeted thermal management. We quantify this relationship using the fundamental conversion factor, where 1 watt corresponds to approximately 3.412 British thermal units per hour. By deriving the total wattage of the installed hardware, we establish the peak sensible heat load, which serves as the primary input for determining the necessary crack or CRA unit tonnage requirements. Calculating the load is only the first step, as the effective distribution of conditioned air is where many designs technically fail. Even if your cooling units have enough total capacity, improper airflow management can create lethal hotspots that trigger thermal shutdowns in localized server racks. We typically address this by implementing containment strategies, such as the hot aisle and cold aisle arrangement, which serves to segregate the supply air from the exhaust air. To maximize the efficiency of these systems, we install blanking panels in open rack spaces to force air through the equipment rather than around it. Furthermore, In environments utilizing raised floors, we must calculate the necessary cubic feet per minute flow rates to ensure that perforated tiles deliver the required volume to the intake side of the equipment. These calculations often involve a delicate balance of static pressure management, as excessive pressure loss under a raised floor can lead to suboptimal delivery at the end of the supply rows. Human occupation and lighting also contribute to the total heat load, though in a modern, highly dense ICT environment, these values are often negligible compared to the massive power draw of the active hardware. When we account for personnel, we typically estimate a sensible heat gain of a few hundred BTU per hour per occupant, which is statistically insignificant when compared to a single chassis generating several kilowatts. Nevertheless, an RCDD must be thorough in every calculation, incorporating the inefficiencies of power distribution units and uninterruptible power supply systems into the total thermal budget. AUPS is never perfectly efficient, and the energy loss during the conversion process is dissipated as heat within the room itself. By aggregating the total electrical load, including the inevitable efficiency losses, we define the minimum thermal rejection requirement. We then cross-reference these requirements against the ASHRAE standards for temperature and humidity to ensure the equipment operates within the specific reliability curves specified by the manufacturers. Designing for thermal reliability requires a commitment to rigor that separates a functional space from a source of expensive equipment failure. Maintaining strict control over the intake temperatures at the server level is the ultimate objective of every design element we have discussed. If the airflow bypasses the intakes, or if the heat rejection units are positioned without considering the fluid dynamics of the room, you will encounter localized thermal excursion events. Our goal is to create a predictable environment where the thermal load is matched by a corresponding, well-distributed cooling capacity that respects the architectural constraints of the facility. As you look at your own design documentation, always remember that thermodynamic reality governs the lifespan of the assets you are installing. By ensuring that your British thermal unit requirements are satisfied through proper CFM delivery and effective containment, you provide the foundation for a stable and long-term networking environment. I hope this technical overview helps you master these demanding calculations. Catch you in the next lecture. Welcome back. In this lesson, we begin our exploration of outside plant design by addressing the fundamental principles and rigorous site assessment methodologies required for exterior infrastructure. Designing for the outside plant environment is fundamentally different from internal cabling because you are transitioning from a controlled, predictable space into an unpredictable, hostile, and highly regulated landscape. The primary challenge in this domain is the intersection of physical geography and complex legal frameworks that govern how we traverse public and private land. Your role as a designer starts long before a shovel hits the ground, specifically with a comprehensive site survey and route analysis. You must account for soil composition, which significantly impacts the difficulty of excavation, and establish the local frost line to ensure all subterranean infrastructure is placed at a depth that prevents frost heave from damaging the conduits. Furthermore, the water table level can influence the choice of materials, as high moisture content in the soil often necessitates the use of gel-filled or water-block cabling to prevent liquid ingress. By mastering these environmental variables, you create a robust physical layer that can withstand years of exposure to elements that interior systems never encounter. Navigating the legal constraints of right-of-way acquisitions and multi-jurisdictional permitting is arguably as important as the physical cabling choice. Before any engineering design is finalized, you must secure the legal authority to place your infrastructure either through easements, existing utility conduits, or negotiated access agreements. This process often involves extensive coordination with municipal authorities, state departments of transportation, and private landowners, each with their own set of requirements. You are essentially acting as a project manager who understands the technical, legal, and financial weight of every foot of cable laid. When dealing with existing subterranean utilities, compliance with local directives like the 811 dig safe coordination is non-negotiable. And in complex urban environments, you may need to employ ground-penetrating radar to verify the locations of gas, water, and electrical lines that may not be accurately reflected in historical records. Ignoring these risks not only threatens the safety of the construction crew, but can lead to catastrophic project delays and legal liabilities. At the architectural level, OSP design requires a strategic decision regarding the topology of the network, choosing between ring, mesh, or star configurations based on the desired level of redundancy and cost. A star topology is often simpler to manage, whereas a mesh structure provides the high resiliency required for mission-critical campus backbones, where a single fiber cut cannot result in downtime. Once the topography is set, you must carefully evaluate the trade-offs between fiber optics and high pair count copper for your backbone links. While fiber is the standard for long-distance, high-bandwidth applications due to its immunity to electromagnetic interference and attenuation characteristics, copper may still find limited utility in specialized control applications or short-range power-limited circuits. You are tasked with analyzing the economic impact of your decisions, specifically comparing the high initial costs of trenching, which provides superior protection, against the efficiency of horizontal directional drilling in developed areas where surface disruption must be minimized. Building a resilient communication link across an exterior landscape requires balancing the tension between financial investment and the physical survival of the plant. You need to treat the design as a lifecycle investment where maintenance, future upgrades, and potential physical hazards such as rodents or construction activity are accounted for at the planning stage. This means selecting materials that are rated for the environment, ensuring that cable jackets are resistant to moisture, UV radiation, and mechanical stress. The methodology of OSP design essentially boils down to creating a path of least resistance through a myriad of physical, financial, and legal obstacles. A successful design ensures that whether the cable is buried or aerial, it remains protected and accessible for necessary repairs, thereby securing the integrity of the data it carries. By internalizing these foundational methodologies, you are better equipped to handle the specific installation techniques that follow in subsequent discussions. I will see you in the next lecture. Hello, and welcome to this session on the technical rigors of outside plant design. We are now diving into the specialized domain of aerial cable installations, where the physical environment dictates every engineering decision we make. Designing an aerial pathway requires a fundamental understanding of mechanical load distribution, as these cables are subjected to forces that are largely absent in indoor environments. You must first address the physics of sag and tension, as the messenger wire, typically a stranded steel cable, must support the weight of a telecommunications plant while maintaining sufficient clearance. The tension in these spans is dynamic, influenced heavily by ambient temperature, wind loading, and the cumulative weight of ice accumulation. In heavy loading districts, as defined by meteorological data, the ice and wind loads can be catastrophic if the poles are not analyzed for their total structural capacity. The designer's objective is to calculate the initial tension so that, after creep, the permanent elongation of the messenger over time, the finalized sag remains within the prescribed limits. We calculate these values using the parabola equations for spans, ensuring that the messenger operates well within the elastic limit of the material to prevent failure during severe weather events. Structural integrity relies heavily on the pole loading analysis, which is the process of calculating the combined stress exerted by all attachments on a utility pole. Every cable, splice case, and hardware component introduces a load that must be accounted for against the pole's inherent braking strength. When we add fiber slack loops, often managed by snowshoes, we are adding both dead weight and surface area for wind loading, necessitating a recalculation of the moment force at the ground line. The use of guy wires and anchors is essential to counteract the tension forces at dead ends, corners, or uneven spans. These structural support systems must be designed to direct the resulting forces safely into the earth, preventing the utility pole from leaning or shearing under stress. Improperly tensioned guys or insufficient anchoring are primary failure points in storm-stressed aerial plants, so the selection of the correct guy strand diameter and anchor type is a critical engineering task. Safety and regulatory compliance form the non-negotiable bedrock of aerial design, specifically concerning clearance requirements mandated by the National Electrical Safety Code, or NESC. You are required to maintain strict vertical separations from ground surfaces, including roadways, railways, and pedestrian paths, to protect both the facility and the public. Equally vital is the horizontal and vertical separation from energized power conductors. High-voltage power lines induce electromagnetic fields, but the more immediate danger is physical contact. which necessitates mandatory minimum clear distances to prevent arc-over incidents. During the make-ready engineering phase, the designer coordinates with power utility providers to ensure that all attachments maintain these critical clearances. This process often involves shifting existing utility assets to create the required space for the new telecommunications plant, a task that requires meticulous documentation and field verification. Hardware selection and implementation strategy are the final pieces of this design puzzle. Suspension clamps, which secure the messenger to the pole, must be rated for the expected load and provide structural stability without damaging the messenger's integrity. For fiber optic deployments, slack storage is managed through circular snowshoes, which ensure the minimum bend radius of the fiber is strictly maintained while providing enough length for future splicing and repairs. Splice cases must be rated for outside plant environments, meaning they must be impervious to moisture, ultraviolet degradation, and mechanical vibrations. By integrating these components into a coherent, load-balanced design, the engineer creates a deployment that is not only functional, but also resilient against the inevitable environmental stressors of an outdoor landscape. See you in the next lesson. Welcome back to the course. Today, we will examine the rigorous technical requirements and physical deployment strategies associated with direct buried cabling systems. When we transition from controlled interior environments to the unpredictable domain of direct burial, our design philosophy must shift toward extreme physical hardening. The primary objective is to maintain signal integrity while shielding the cable from the crushing forces of soil displacement, moisture ingress, and biological threats. Before a single foot of cable hits the dirt, you must account for frost lines, as the soil expansion and contraction cycles typical in colder climates can impart significant mechanical stress on telecommunications infrastructure. Trenching depths are not merely recommendations. They are critical safeguards against accidental excavation damage and seasonal thermal shifts. In most jurisdictions, you will find that burying cables below the local frost line is mandatory to ensure long-term stability and prevent the premature failure of the cable jacket or internal components. Once the trench is excavated, the interaction between the soil composition and the cable jacket becomes a primary concern. Raw, rocky earth is the natural enemy of high-performance fiber or copper, as sharp inclusions can easily lacerate or puncture the outer sheath. To mitigate this risk, we employ a sand bedding layer, which provides a neutral, compliant interface between the harsh native soil and the cable itself. This fine-grained material acts as a mechanical buffer, distributing localized point pressures evenly across the surface of the jacket rather than concentrating them on a single protrusion. Above this layer, the installation of detectable warning tape serves as a vital last line of defense, providing a clear visual and magnetic warning to future excavators. This tape should ideally be placed several inches above the cable to ensure it is intercepted well before any heavy machinery makes contact with the actual communication lifeline. The cables themselves must possess intrinsic defenses against these subterranean hazards, leading us to utilize specific material configurations like corrugated steel tape armor. This metallic layer provides high crush resistance, which is essential when the weight of the overhead ground is factored into the long-term strain on the cable. Beyond the metal armor, heavy-duty, high-density polyethylene jackets are standard because of their chemical inertness and resistance to environmental degradation. To combat the pervasive threat of water, manufacturers incorporate swellable yarns and water-blocking gels within the cable structure. These materials are designed to expand upon contact with liquid, effectively sealing any microscopic breach in the jacket and preventing moisture from migrating down the length of the conduit or cable core. This is especially important for protecting metallic elements from corrosion and fiber optics from potential micro-bending losses induced by hydrostatic pressure. Deployment logistics often define the difference between a successful project and a maintenance nightmare, particularly when using cable plowing operations. Unlike trenching, where the ground is opened and backfilled in two distinct steps, plowing utilizes a specialized blade that slices through the earth, simultaneously laying the cable at the correct depth. While this is efficient for long, straight runs, it requires precise calibration to prevent the cable from being stretched beyond its rated pulling tension. Should your route encounter subterranean obstacles like large boulders or intersecting utility lines, the plowing mechanism must be adjusted to navigate safely. Calculations for pulling tension are paramount here, as exceeding these limits can permanently damage the internal geometry of optical fibers or the twist characteristics of copper pairs. leading to intermittent signal degradation that may not immediately manifest as a total outage. When it comes to the connectivity of these buried segments, the splice enclosure acts as the critical nexus point for environmental isolation. Buried enclosures must be rated for the expected hydrostatic pressure and chemical exposure they will face over a multi-decade life cycle. Furthermore, if you are utilizing armored cables, you must ensure localized grounding of the metallic sheath, as these elements can become pathways for galvanic corrosion or unwanted electrical currents. This requires dedicated bonding to an earth ground system that is distinct from the primary building ground, yet structurally sound enough to mitigate surges. Finally, no direct buried design is complete without the meticulous application of GIS mapping to document the exact path of the cable. As the landscape changes or subsequent utility work occurs, accurate documentation will ensure that your hardened infrastructure remains invisible to the world but fully accessible to those responsible for its maintenance. I will see you in the next lecture. Welcome back. Today we examine the intricate engineering requirements for underground conduit systems and maintenance hole deployments in outside plant environments. Designing underground infrastructure requires a shift in perspective from typical interior space planning to a much more rigorous civil engineering mindset. When you commit to a subterranean path, the permanence of your decision places a heavy burden on initial accuracy and foresight. You are not simply running a cable. You are creating a long-term utility corridor that must withstand massive environmental stresses. The primary objective in this discipline is to protect the fiber optic assets from physical damage while ensuring they remain accessible for future growth. A conduit pathway that is improperly sized or poorly placed today becomes a costly, unfixable liability once the concrete sets and the earth is backfilled. Concrete encased duct banks represent the gold standard for secure OSP architecture, providing both mechanical protection and stability for the conduit runs. When designing the geometric configuration of these banks, we must look at the duct matrix, which refers to the physical arrangement of the conduits within the concrete envelope. A common error is failing to account for the necessary spacing between conduits, which is essential to ensure the concrete slurry properly encapsulates every pipe without leaving voids. You must consider the thermal dissipation properties of your layout, especially when multiple high-density fiber bundles are expected to generate heat over time. Furthermore, the use of inner ducts within the primary raceway allows for a subdivision of space that dramatically simplifies future cable deployments. By utilizing fabric mesh dividers or pre-installed inner ducts, you essentially future-proof the pathway, permitting a new technician to pull a fresh fiber strand without disturbing the existing live traffic. Before any cable is pulled into an underground system, we must address the physics of the install, specifically the mathematics of pulling tension and sidewall pressure. A cable is governed by strict mechanical limits provided by the manufacturer, and exceeding these during the installation phase will cause irreparable damage to the fiber optics. We calculate the maximum allowable pulling tension based on the cable's design, but this number is an abstraction that holds no weight until we account for the system geometry. Every sweep, bend, and transition in the conduit path introduces friction, which acts cumulatively to increase the force required at the winch. Sidewall pressure is an equally critical metric, specifically measured at the bends where the cable is pulled tight against the inner radius of the duct. If the bend radius is too sharp, the pressure against the conduit wall can crush the fiber buffers. We must therefore ensure that the conduit sweeps comply with the prescribed minimum bending radius for the installed medium. Maintenance holes, or MH systems, serve as the critical access points in this subterranean network, acting as the nexus for cable slack storage and splicing organization. These structures must be designed to accommodate the H20 traffic loading standard, which defines their ability to withstand the weight of heavy vehicles passing overhead. When selecting and specifying these precast units, you are looking at more than just the internal volume. You must plan for the placement of racking hardware to keep the cables neatly organized along the walls. The racking arrangement is vital because it determines the size and accessibility of the slack loop, which is necessary for future troubleshooting or repairs. We also cannot overlook the inclusion of a sump pit, which is mandatory for the removal of groundwater that inevitably seeps into these cavities. Proper slope specifications for the conduit entries into the MH, usually toward the structure, are required to facilitate natural drainage and prevent water from backing up into the duct bank system. Professional, systematic documentation of these subterranean pathways is what separates a novice design from a truly resilient OSP project. You should think of the route planning as a blueprint for long-term scalability, where every conduit subdivision and maintenance hole position is mapped with extreme precision. The goal is to reach that impenetrable status alluded to in the standards, where the physical layer is so robust that maintenance and expansion involve only minor, controlled interventions rather than mass excavation. By calculating the coefficient of friction correctly and choosing the appropriate lubricants, you ensure that the cable slides through the conduit segments according to the design plan. Remember that the lubricant volume is not a guessing game. It is a calculated variable based on the total surface area of the cable and the internal diameter of the duct, aimed at reducing the dynamic friction to safe levels. Through these systematic calculations, you build a foundation that supports data transmission for decades to come, independent of the external environment. I will see you in the next lecture. Welcome back. In this lecture, we examine the complexities of outside plant route planning and the engineering rigor required for geographic connectivity. When we approach the design of an outside plant route, we are essentially performing a balancing act between mathematical efficiency and physical reality. The objective is to identify a path that minimizes total trenching or aerial footage while adhering to the inherent survivability requirements of a mission-critical campus network. We must differentiate between the shortest path, which reduces material costs and latency, and the most survivable path, which prioritizes geographical diversity. Designing for extreme survivability often dictates that we implement redundant entry points into buildings, ensuring that a physical cut on one side of the campus does not isolate the facility from the primary network core. By eliminating single points of failure at the design phase, we prevent catastrophic outages that would otherwise arise from localized excavations or unforeseen infrastructural failures. This process requires a sophisticated understanding of topology and a refusal to settle for the path of least resistance when that path introduces unacceptable risk to the link's integrity. Navigating topological obstacles requires more than simple mapping. It demands an intimate familiarity with civil engineering constraints that often dictate the viability of our design. Crossing a river, for example, necessitates a choice between bridge attachments, which are often subject to strict load-bearing and thermal expansion requirements, and directional boring underneath the riverbed. Each method carries different costs regarding permitting and environmental impact studies, particularly when dealing with protected waterways. Railway bores represent another significant hurdle, as these require intensive coordination with transit authorities, strict safety protocols, and often deep bore equipment to avoid disrupting the structural stability of the tracks. We must also account for existing subterranean utilities, where the presence of high-pressure gas lines or fiber optic long-haul backbones can render a theoretically optimal route physically impossible to construct. Every obstruction is a variable in our cost model that must be accounted for before a single shovel enters the ground. The bureaucratic component of OSP route planning is arguably as critical as the physical construction, as local ordinances and federal regulations can halt a project indefinitely if overlooked. Coordination with municipal departments, the Department of Transportation, and the Environmental Protection Agency is not a mere formality, but an active component of the route design. Traffic control plans must be meticulously developed to accommodate lane closures during trenching or pole settings, which often necessitates working during off-peak hours to minimize public impact. Furthermore, successful route planning involves the sequencing of construction phases so that we maintain network continuity if we are upgrading legacy segments. We use these interactions to secure land use agreements and right-of-way permissions that are essential for long-term project stability. Failing to harmonize our technical requirements with these regulatory frameworks is a frequent cause of budget overruns in major industrial and campus infrastructure projects. Modern OSP design relies heavily on the integration of geographic information system data to transform raw site surveys into construction-ready documentation. By leveraging GIS coordinates, we can visualize the projected route against existing utility maps and topographical layers with millimeter-scale accuracy. These drawings must provide clear instructions for bore depths, conduit encasement types, and the specific coordinates for splice points or manholes. Construction drawings are the primary communication medium between the RCDD designer and the field crews. Therefore, they must be unambiguous to prevent field-driven changes that could compromise the design's survivability. An optimized route is one that has been vetted through spatial analysis to ensure that every trench, pull box, and connection point is both legally permissible and physically viable. Our goal is to minimize field-directed RFI activity, which in turn reduces the likelihood of costly change orders and ensures the project remains within the desired economic and temporal parameters. See you in our next session. Welcome back to the RCDD journey, where we turn our attention toward the resilient infrastructure required for outside plant environments. This lesson focuses on the rigorous material selection standards necessary to ensure long-term physical integrity in harsh exterior conditions. When we transition from the controlled environment of a telecommunications room to the outside plant, the materials we choose must withstand forces that would rapidly degrade standard indoor products. The primary adversary in this domain is environmental exposure, specifically ultraviolet radiation and moisture. Standard cable jackets utilize polyethylene compounds that are inherently susceptible to long-term UV degradation, which causes brittleness and eventual cracking. To combat this, OSP-rated cables must employ carbon black additives within the jacket material to provide the necessary UV resistance and chemical stability. Furthermore, external moisture ingress is a persistent threat to signal integrity in both copper and fiber media. To counter this, we rely on hydrophobic water-blocking compounds, such as gel-filled buffers or dry water-swellable powders, which react upon contact with moisture to seal the breach. These components are not optional. They are fundamental requirements for surviving the standard 20 to 30-year life cycle expected of OSP infrastructure. The physical hardware supporting these spans requires equally robust engineering, particularly when considering the inevitable onset of galvanic corrosion in earthen environments. For subterranean or aerial hardware, we typically mandate the use of 300 series stainless steel or hot-dip galvanized components to maintain structural load-bearing capacity. When selecting splice closures, the requirement shifts toward hermetic sealing, as these components often reside in maintenance holes that are prone to flooding or high humidity. A hermetically sealed closure must maintain a defined pressure equilibrium to prevent the internal air volume from expanding and contracting with temperature fluctuations. If the seal fails, the resulting pressure equalization draws moisture directly into the splice point, which is catastrophic for fiber optic ribbons or high pair count copper terminations. Therefore, specifying the correct sealing mechanism and checking the manufacturer's ingress protection rating is a critical task for any designer. Addressing the capacity requirements of modern networks often leads us to high-density deployments, such as 3,456 fiber count ribbons, which require specialized splicing logistics. Within the confined spaces of a subterranean maintenance hall, managing this fiber density requires a disciplined approach to slack management and splice tray selection. We must verify that the chosen splice module is compatible with the specific fiber coating and ribbon geometry to avoid attenuation spikes caused by mechanical stress. For copper-based OSP, PIC cable color codes and heavy pair count splice modules remain standard, yet they present their own set of unique installation challenges. These heavy cables are difficult to manipulate, and the designer must ensure that the cable transition into the splice closure does not violate the minimum bend radius requirements during the splicing process. Failing to account for the physical footprint of these cable bundles often results in damaged conductors or fractured fiber ribbons during the final closure seal. Beyond the cables and splices themselves, the localized environment often demands the deployment of specialized cabinets, cross-connect pillars, and environmentally controlled pedestals. These enclosures serve as the interface between the core network and the periphery, meaning they must protect sensitive electronic equipment from seismic shifts and thermal cycling. A designer must evaluate the site-specific soil conditions and ambient temperature extremes to determine if active cooling or heating is required within the pedestal. Furthermore, every metallic enclosure must be integrated into a dedicated localized grounding grid to redirect transient surges and maintain safe touch potentials. This grid, consisting of grounding electrodes and bonding conductors, must be robust enough to handle high-energy events, as OSP equipment is often the first point of contact for lightning-related strike paths. By meticulously selecting these hardened components, we create an infrastructure that remains unyielding in the face of mechanical abuse and environmental volatility. See you in the next lecture. Welcome back. In this chapter, we explore the essential administrative rigor required to translate complex engineering designs into binding contractual obligations. The request for proposal, or RFP, serves as the definitive bridge between your engineered vision and the reality of the physical installation. When you prepare these documents, you are not merely writing a request for services, you are crafting a legal instrument that governs project scope, financial liability, and quality benchmarks. The primary objective is to eliminate ambiguity, as any unclear language becomes a potential loophole for contractors to exploit. This often leads to change orders, budget overruns, and scheduling delays that reflect poorly on the designer. Your documentation must be exhaustive, providing enough detail that a qualified bidder can translate your drawings into a complete bill of materials without having to make assumptions about your intent. To maintain consistency across the construction industry, we utilize the Construction Specifications Institute master format. This standardized organizational structure ensures that all parties involved in a project understand where to find specific technical requirements. Specifically, we focus our attention on Division 27, which covers communications, and Division 28, which covers electronic safety and security. By adhering to this structure, you ensure that your cabling, pathways, and security systems are categorized in a way that aligns with the rest of the construction contract. If you fail to follow this format, you risk excluding critical components from the contractor's scope, which inevitably leads to disputes regarding who is responsible for the funding or labor of those overlooked items. Technical specifications form the core of the bidding process and demand precise language concerning materials, methods, and quality. You must clearly outline the material submittal requirements, such as requiring data sheets for every cable, connector, and patch panel before ordering occurs. Quality assurance mandates are equally vital, as they define the standards for contractor certification, specialized training, and required field testing. You should also explicitly state warranty conditions, defining the specific requirements for system warranties against defects in both materials and workmanship. When you demand proof of manufacturer training for technicians, you are directly protecting the owner from substandard installations that would otherwise jeopardize the long-term performance of the communications infrastructure. Translating design drawings into a precise bill of materials is a task that leaves no room for error. Every cable run, outlet, and equipment rack must be accounted for to ensure that the bidding process remains competitive and accurate. When creating your contractual language, avoid using vague terms like industry standard without providing the specific TIA or ISO reference where that standard is formally defined. If you lack a clear requirement for how a pathway must be supported or how telecommunications rooms must be finished, you are leaving the quality of the end product to the discretion of the lowest bidder. Instead, write ironclad requirements that prioritize the physical realization of the design as specified in your construction drawings. Risk mitigation requires a robust pre-qualification process and the strategic use of bonding. You must decide whether to require bid bonds to guarantee the contractor will honor their proposal, as well as performance and payment bonds to protect the owner against non-completion or non-payment of subcontractors. These instruments are not just bureaucratic formalities. They are your primary defense against contractors who lack the financial stability to fulfill the contract. Without these protections, an owner could be left with an incomplete project and liens placed against their property. Always define these requirements early in the documentation phase so that all bidders have equal opportunity to integrate these costs into their submissions. Finally, the integrity of your selection process relies on the establishment of an objective evaluation matrix. You should define the weighting criteria for bidders based on factors like technical competency, previous experience on similar projects, and cost-effectiveness. By documenting these criteria, you remove subjectivity from the selection process, which is critical if you are ever asked to justify why a specific contractor was chosen. A well-constructed RFP does not just ask for a price. It asks for a comprehensive execution plan that demonstrates the contractor understands the complexity of the project. When you provide this level of detail, you ensure that the project is executed precisely as you engineered it, on time, and within the agreed budget. See you in the next session. Welcome back. In this chapter, we focus on the transition from blueprint to job site by mastering the rigorous processes of bidding and performing detailed site surveys. The bidding phase represents the point where your design is scrutinized for viability and cost, making it the most vulnerable stage for project integrity. You must understand that a successful bid process relies on transparency and absolute clarity in your documentation to prevent scope creep later on. When you organize a pre-bid meeting, your primary objective is to ensure that all potential contractors have an identical baseline understanding of the project requirements. If a contractor asks a question, that information cannot remain private. You are obligated to issue a formal addendum to every participant to ensure a level playing field. This is not merely a formality, but a legal necessity that prevents claims of favoritism or misinterpretation. When evaluating the submitted packages, you are looking for more than just the lowest price, as a suspiciously low bid often signals an unbalanced bid or a misunderstanding of the complexity of the installation. A professional designer must be able to identify signs that a contractor is underbidding, which eventually leads to change orders that destroy the project budget. Your scrutiny here acts as a filter to keep only qualified, capable entities on the final list. Transitioning to the physical site survey, you are moving away from the safety of the office environment into the reality of the structure. The core philosophy here is to reconcile what is drawn on paper with what exists in the physical space, as blueprints rarely account for the nuance of an aging building. You must look for structural anomalies that were not captured during the initial architectural design phase, such as unforeseen load-bearing obstructions or low ceiling heights that limit tray capacity. It is also your responsibility to scan for hidden hazards, like legacy asbestos insulation or lead-based paint, which can halt a project indefinitely if encountered during the actual installation. You need to investigate the existing HVAC capacity in telecommunication spaces, because a room designed for legacy equipment often lacks the cooling for modern high-density hardware. Furthermore, verify the existing grounding grid to ensure that any proposed pathways will not interact negatively with current electrical installations. This phase of the project is often quiet and tedious, but it is precisely where you prevent the catastrophic errors that lead to mid-project redesigns. Practical tools are your best allies during these surveys. Never venture into a site without a laser measurer and a capable camera. A laser measurer provides the precision required for determining exact cable pathway lengths, which directly impacts signal loss and material calculations. Using a 360-degree camera allows you to capture the complete context of a room, ensuring you can review the ceiling conditions or wall penetrations later when you are finalizing your designs. For areas where underground pathways or concrete slabs are involved, ground-penetrating radar is non-negotiable for identifying buried conduits or rebar that would complicate core drilling. Documentation during this time must be extremely meticulous, as you are likely the last person to have a clear view of the space until the demolition or construction teams arrive. Map out every potential core hole location and record the availability of space in existing conduits, as theoretical capacity is rarely reflecting the actual congested state of older pathways. Being thorough now saves you from the professional embarrassment of discovering an impossible installation trajectory once the project is already underway. Bridging the gap between a set of theoretical blueprints and the reality of a job site is the mark of a skilled designer. When you find a discrepancy, you must document it immediately and communicate it to the facility stakeholders to determine if a design modification is required. This proactive approach prevents the "we can't put it there" conversation that happens when installers reach an impassable wall midday. Always keep in mind that the site survey is an iterative process. If you see a conflict, reevaluate your design, check your codes for alternative routing, and adjust your documentation before the bid even closes. The effort you put into these site meetings and surveys directly correlates to the number of change orders you will have to manage later. By being rigorous, professional, and observant, you maintain control over the project's trajectory from the very beginning. I will see you in the next lecture. Welcome back. In this session, we will examine the financial and operational execution required for successful telecommunications project management. Estimating begins with a comprehensive material takeoff, which requires translating design documents into a precise list of every cabling component, patch panel, and enclosure required for the installation. When calculating labor units, you must move beyond simple industry averages and apply context-specific multipliers to reflect the actual environment. For example, installing category cables in a high-ceiling warehouse or a confined space requires significantly more man-hours than a standard office build-out due to the added difficulty of access and safety compliance. You must also account for the nuanced differences in labor costs, such as the gap between union and non-union rates, as well as the mandate of prevailing wages on public projects. Factor in the logistical overhead of shipping, material staging requirements, and the necessity of on-site security for high-value components before installation even begins. By maintaining a rigorous approach to these variables, you prevent the erosion of your profit margin caused by the common hidden costs of project deployment. Once the estimate is complete, the construction administration phase shifts the focus toward the ongoing orchestration of the installation. A core component of this responsibility is the creation and maintenance of a detailed Gantt chart, which breaks down the installation into granular phases such as the initial rough-in, backbone cabling, final termination, and comprehensive testing. Throughout this life cycle, the designer acts as the primary point of validation, ensuring that the work performed matches the project specifications and contractual requirements. You will be expected to conduct regular site meetings to synchronize expectations between the general contractor and the telecommunications installers. During these sessions, you must review material submittals to confirm that the hardware arriving on site matches the engineering design to prevent costly remediation steps later. This proactive oversight is essential to avoid schedule drifts that often occur when technical discrepancies remain unaddressed for too long. Validating payment applications requires an objective assessment of the actual percentage of completion against the project timeline. This is not merely a manual check of finished outlets. It involves a systemic audit of the physical installation status relative to the billing milestone request. You must ensure that the quality of work meets industry standards before signing off, as the financial leverage you hold during the construction phase is your most effective tool for insisting on excellence. When the installation nears completion, you will lead the punch list process, which is a formal, exhaustive walkthrough to identify aesthetic and functional deficiencies that must be rectified before final acceptance. This includes verifying that pathways are properly supported, Firestopping is correctly installed according to the code, and all terminations are documented and tested against the link loss budget. By maintaining this level of authority, you ensure that the project is not just completed, but completed to a standard of quality that guarantees long-term infrastructure reliability. See you in the next lecture. Welcome to the chapter on construction administration, where we will examine the formal mechanisms of requests for information and the financial scrutiny of change orders. This instructional unit provides the rigorous framework necessary to navigate project friction while ensuring technical compliance. In the reality of any construction project, the transition from architectural design to physical implementation inevitably reveals gaps in documentation or unforeseen field conditions. A request for information, or RFI, serves as the formal instrument for contractors to solicit clarification when design documents appear ambiguous or physically impossible to execute as drawn. As an RCDD, your role is to treat every RFI not merely as a question, but as a critical technical document that carries potential legal weight. When you receive an RFI, you must perform a rapid yet exhaustive analysis of the contract drawings and specifications to determine if the query is a genuine conflict or an attempt to shift blame for an overlooked detail. Your response must be unambiguous, referencing specific codes or TIA standards to justify your position, as vague instructions only invite further requests. If the RFI points to a genuine pathway collision or an equipment clearance issue, your resolution must prioritize the structural integrity of the cabling design while remaining cognizant of the trade sequencing. Always keep in mind that once your response is signed and transmitted, it effectively becomes part of the contract record, which means precision in your professional communication is non-negotiable. If you fail to maintain clear records of these clarifications, you lose the ability to defend your design when budget or schedule discussions inevitably turn hostile. The change order process is perhaps the most adversarial aspect of modern construction, representing a formal modification to the project scope, timeline, or total cost. A change order is rarely a simple affair. It is a calculated negotiation where you must validate the contractor's claims for additional labor and material costs against the reality of the site. When a contractor requests a change, you are obligated to scrutinize the request for validity, distinguishing between legitimate unforeseen site conditions and simple scope creep resulting from poor initial planning or contractor error. You need to verify the math behind the requested price increase, ensuring that the labor hour estimates correlate with industry standards for the specific task at hand. If the request stems from an owner-driven requirement, you must ensure that the change does not violate existing code requirements or compromise the performance metrics of the structured cabling system you have meticulously designed. My recommendation is to always maintain a rigorous documentation trail, including photographs, impact assessments, and justifications that are tied directly to the original contract. By positioning yourself as a gatekeeper of the budget, you protect the client's interests and maintain the project's technical integrity against pressure to accept shoddy work or unjustified markups. This dual focus on technical precision and fiscal oversight is what separates a proficient designer from an expert consultant who can manage the pressures of a complex construction site. Effective design documentation serves as your primary defense against the proliferation of RFI volume and costly change orders throughout the project lifecycle. When you produce high-quality, clear, and comprehensive design sets, you significantly reduce the ambiguity that fuels contractor queries. However, no set of plans is ever perfect, so the ability to respond to inquiries efficiently remains a vital skill for anyone managing large-scale telecommunications infrastructure. When evaluating change orders, remember that your approval hierarchy is your best friend. Never authorize a financial change without ensuring it has traversed the required signature chain within the project management office. This process is designed to prevent unilateral decisions that could lead to systemic failures or legal exposure for the design firm later on. Master the balance between being a facilitator who keeps the work moving and a vigilant guardian who ensures that every dollar spent brings legitimate value to the infrastructure. By maintaining this professional detachment and technical focus, you will navigate even the most contentious project environments with confidence. I will see you in the next lesson. Welcome back, and today we turn our attention to the growing convergence of security and audiovisual systems within the structured cabling environment. This chapter focuses on integrating these non-traditional systems into the telecommunications backbone while maintaining system integrity. In modern facility design, the physical layer infrastructure is no longer solely dedicated to data networking, but must now support a vast array of high-bandwidth sensors and multimedia endpoints. When we incorporate physical security devices like pan-tilt-zoom IP cameras or biometric scanners, we are essentially extending our network to the perimeter of the building. These devices often rely on power over Ethernet to function effectively, necessitating a robust power budget calculation at the switch port level. You must account for the specific IEEE 802.3 standards when dealing with high-draw devices, as failing to factor in the total wattage can lead to intermittent failures in critical security zones. Furthermore, latency sensitivity is paramount in security arrays, requiring that our pathing solutions provide predictable throughput without packet collisions. We do not simply plug these devices in, we treat them as integral, life safety components of the enterprise architecture. Transitioning into the audiovisual domain, we face distinct challenges related to signal integrity and electromagnetic compatibility that differ significantly from standard data transit. High-definition transmission formats such as HD-Base-T or HDMI over IP are highly sensitive to noise-induced jitter, which can degrade display quality or cause catastrophic signal loss during high-load scenarios. When running DANTE audio networks or large-scale matrix video systems, the choice of shielding becomes a critical design variable to prevent high-frequency noise coupling. We must rigorously follow TIA 862 guidelines for intelligent buildings, ensuring our pathways are designed to accommodate the bulk of these cables without exceeding fill ratio limits. If you neglect the physical separation requirements between power conductors and high-bandwidth multimedia cables, you invite interference that is notoriously difficult to troubleshoot after the ceiling is closed. Precision in cable management is not just aesthetic, it is a fundamental requirement for signal stability. The telecommunications room itself must evolve to manage the added stresses of these converged systems, specifically regarding space allocation and thermal management. A standard TR design that ignores the footprint of matrix switchers and massive intrusion detection arrays will eventually suffer from equipment congestion and cooling failures. Each rack unit of space must be accounted for during the planning phase, ensuring that the cabinets themselves can support the structural weight of specialized AV hardware. Dedicated, uninterruptible power supply circuits must be sized not just for nominal loads, but for the worst-case power draw of all security and AV hardware residing within that room. We must coordinate extensively with external security consultants and AV integrators early in the design phase to avoid redundant cabling or, worse, undersized pathways. When we unify these systems under a single design mandate, we ensure physical robustness that spans from the backbone to the most edge-based security sensor. See you in the next lesson. Welcome to our deep dive into building automation system networks, where we will examine the integration of intelligent building components into the core telecommunications infrastructure. The shift toward intelligent building architecture necessitates that designers treat building automation systems, or BAS, and Internet of Things endpoints as primary components of the physical layer. We are moving away from siloed mechanical systems toward a converged network model, where HVAC controllers, BASnet protocols, Modbus arrays, and lighting control systems share the same pathway infrastructure as traditional data networks. This integration forces a reevaluation of how we manage low-voltage power and data distribution across thousands of ceiling-mounted sensors and occupancy monitors. When we incorporate devices like temperature and humidity sensors, we are essentially building the nervous system of the structure. The challenge lies in designing a resilient physical layer that can accommodate these high-density requirements without compromising the performance of the standard telecommunications backbone. By treating these endpoints as first-class citizens in our designs, we ensure the infrastructure remains scalable and capable of supporting the autonomous functions that define modern smart buildings. Designing for this density requires a robust zone cabling architecture that leans heavily on consolidation points and telecommunications enclosures to keep link distances within manageable parameters. Relying on a traditional home-run topology from a central telecommunications room to every individual IoT device is rarely efficient or cost-effective in a massive sensor grid. By deploying consolidation points in the ceiling space, we create a flexible interface that allows for simpler moves, adds, and changes, particularly when lighting control arrays or sensor arrays need to be reconfigured. Furthermore, telecommunications enclosures act as critical nodes that bring switching and power distribution closer to the edge, reducing the sheer volume of cabling that must return to the main room. This tiered approach is essential for maintaining signal integrity and power stability across a vast physical floor plan. Proper placement of these enclosures ensures that our low-voltage power budget is managed locally rather than being subjected to excessive voltage drops over long copper runs. One of the most consequential aspects of this transition is the reliance on power over Ethernet to drive these remote devices, which puts significant pressure on our cabling infrastructure. We must strictly adhere to the IEEE 802.3bt standards, specifically looking at Type 3 and Type 4 implementations that provide higher wattage to support sophisticated IoT hardware. Delivering this level of power over traditional twisted pair copper cables introduces the unavoidable physics of thermal heat rise, especially when cables are bundled tightly together in trays or conduits. As heat increases, insertion loss also increases, which can lead to data transmission errors or, in extreme cases, permanent damage to the insulation properties of the cables. To mitigate these risks, the modern RCDD must specify cables with higher temperature ratings or ensure that the bundle sizes are strictly limited according to recognized industry guidelines. We also look toward limited power or LP-rated cables, which are specifically designed to handle the thermal load associated with higher current carrying capacities without requiring the complex manual derating calculations that would otherwise be necessary. In addition to cable selection, the method of termination at the work area or the device location plays a critical role in the overall health of the BAS network. Field-terminated modular plug, terminated links, or MPTLs, have become a standard solution when connecting directly to devices that do not have traditional patch panel interfaces, such as security cameras or specialized environmental sensors. By terminating the horizontal cable directly into a plug, we eliminate the need for an additional modular jack and patch cord, which effectively removes a potential point of failure and reduces the overall insertion loss of the link. However, this demands a high level of craftsmanship during installation because there is zero room for error when field terminating high-performance copper media. Every connection must be tested and validated to ensure it meets the transmission performance requirements expected of the broader network. As we architect these infinitely scalable systems, we are not just installing wire, we are creating a thermally resilient and electrically stable foundation for the intelligent buildings of the future. I will see you in the next lecture. Welcome to the final installment of our Masterclass, where we synthesize our entire journey into a singular engine for exam success. This lesson serves as your terminal checkpoint for mastering the totality of the Telecommunications Distribution Methods Manual. Reaching this stage implies you have processed the granular details of space planning, pathway topologies, and transmission physics. We must now move beyond rote memorization of individual standards toward a fluid, holistic grasp of the infrastructure design process. The RCDD examination is not merely a test of technical recall. It is a trial of your ability to apply TIA, ISO, and NEC frameworks under significant temporal pressure. You should now be able to visualize the interdependencies between a project's architectural constraints and the resulting cable plant requirements. If you have followed the trajectory of this course, you understand that every conduit count, every grounding busbar placement, and every heat load calculation serves a unified purpose of system reliability. When you encounter complex scenarios on the exam, your first step is to strip away the contextual noise and identify the governing standards. Consider the interplay between NEC requirements for electrical safety and the TIA 568 series for structured cabling performance. If a question asks about conduit fill ratios, your brain should automatically reach for the appropriate table based on the fill percentage constraints and cable diameters. Similarly, when presented with outside plant scenarios, you must be prepared to alternate between aerial structural requirements and NESC safety clearances without hesitation. The ability to switch contexts rapidly is exactly what distinguishes a seasoned designer from one who merely understands the theory at a surface level. In terms of mathematical rigor, your proficiency with link loss budgets and voltage drop calculations must be second nature. You are expected to account for every connector pair, whether it is a fusion splice or a mechanical termination, and verify the total decibel loss against the equipment's dynamic range. Do not fumble with basic arithmetic. Instead, focus on the logic of the attenuation budget and the impact of environmental factors like cable temperature on transmission performance. Practice identifying the limiting factors in a design, such as maximum horizontal channel length versus allowable insertion loss. When these numeric constraints are applied to real-world scenarios, the correct answer usually reveals itself through the process of elimination. Project administration represents the final layer of your mastery, requiring you to bridge the gap between technical design and field execution. You should be familiar with the life cycle of an RFI, the necessity of accurate site surveys, and the legal weight of change orders in a construction contract. Whether you are addressing fire-stopping requirements that conflict with the mechanical raceway trajectory or navigating the complexities of a request for proposal, the core objective is always to ensure the physical layer meets client expectations. Think of these administrative tasks as the project management framework that protects your design integrity from the first spade in the ground to the final handover. Precision in this area ensures that you are seen as a peer to the electrical engineer and the architect. As you approach the examination, remind yourself that the syntax of the manual is intentional and precise. The RCDD credential values standardization above all else, so avoid the temptation to apply anecdotal field experiences if they contradict the published TDMM methodologies. Many candidates falter because they attempt to use their own regional interpretations of safety or grounding rather than the universally accepted standards provided in our course documentation. Trust the manual, stick to the vetted workflows, and rely on the systematic approach we have built throughout these modules. Your preparation, when applied with a cool head and a disciplined focus, is more than sufficient to navigate the traps set by the examination board. We have covered the spectrum from core transmission physics to the administrative intricacies of modern building automation. You now possess the analytical tools to dissect any infrastructure problem, no matter how convoluted the scenario presented on the screen. Take confidence in the fact that your knowledge is cumulative and that you are arriving at the exam with a comprehensive architectural understanding of the field. The path to becoming an RCDD requires a dedication to excellence that you have demonstrated by sticking with this program to its completion. You are now prepared to operate at the elite tier of telecommunications design. I wish you the best of luck on your examination. See you in your career as a professional designer.